Hello, everyone. Welcome to the June 2021 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. So this is the coming out of pandemic time period that we're in right now. Hope people are getting vaccinated, being able to resume their lives again a little bit. Jennifer and I, both fully vaccinated, slowly starting to do things that we weren't doing before. Before you could go to some restaurants, at least here in LA, I don't know what it was like different parts of the world. Some restaurants, if they had open outside seating, then there was a little bit where you could go. But now we're able to go to some of our old favorite restaurants that are reopening again. We even went to a movie in a movie theater. We have not yet gotten on a plane. I know that some people were getting on planes, of course, all along, trying to take precautions, but we didn't have any strong needs to go anywhere, so we haven't been on a plane in over a year. I don't have a plane trip planned until, I think, July or something like that, maybe August. So that'll be something. I hope I can remember everything. I did notice that my passport had expired, so I got to get that fixed. All of the crap that is involved with coming back to the real world. Overall, it's very much worth it, but woof, there's a lot of stuff you got to get done. Other than that, yeah, no news from around here, really. I am looking forward to answering these questions. We got a lot of questions. As you know, as if you're veterans, then we get questions from people on Patreon who support the Mindscape podcast with a pittance each week. And they're the ones who are allowed to ask questions. In the old days, when we were a small elite group, I would answer every single question, but it became too big for that. So we have a new system now where I pick questions to answer and group ones together if they're similar thematically. Once again, this month, there were far too many good questions for me to answer. So if I don't answer your question, it's because I don't have anything interesting to say about that. Like, you're very welcome to ask questions of the form, did you read this book and what did you think about it? But if I didn't read the book, I'm not going to answer the question. I'm just going to leave that out deleted. So it's not you, it's me if I'm not answering your question. But if you're listening to these questions being answered and you're burning up with jealousy, saying, boy, I wish I could ask a question and have that be answered, you can support Mindscape on Patreon. Go to patreon.com/Sean M. Carroll. $1 a week, something like that, would be more than enough to let you be part of this community. You get ad-free versions of the podcast, plus you can ask AMA questions. Let's get to answering them. Let's go. Rainer Glüge asks a priority question. So remember, the other rule for Patreons asking questions is if there's some question that is really important to you, you don't want it to get left out because I don't pick it to answer the questions that month, then you just label it priority question, and I promise to answer it, but you're only allowed to do that once in your life. So make it good when you ask a priority question. So Rainer says, can you please explain what happens to photons that don't arrive anywhere due to the cosmic expansion? I understand that the light wave gets redshifted, but is there a limit? So no, there is no limit. The universe keeps expanding. Photons keep getting redshifted. Now, I do have to be a little bit careful, depending on how technical you want to be here. What do you mean by redshifted? Okay, when you emit a photon, it has a certain wavelength in the rest frame of whatever emitted it, right? Whatever atom or galaxy or whatever emitted the photon, you can talk about what the frequency was or the wavelength with respect to that emitter, because that defines a rest frame. In another rest frame, with respect to something that is moving rapidly with respect to the emitter, the wavelength will look different, right? So keep that in mind. When you absorb the photon, you also have to take into account the rest frame of whatever is doing the absorbing. Otherwise, there'll be a blue shift or a red shift just from the Doppler effect. So cosmologically, we can always talk in a somewhat sensible way about the redshift because there is a rest frame, because there is basically a common rest frame of all the galaxies and all the stuff in the universe. They move at a few hundred kilometers per second with respect to each other, but that's nothing compared to the speed of light. So for all intents and purposes, it's a common rest frame. So when you say the photon gets redshifted, you have to tell me what rest frame you're talking about. Once the universe is empty and there's nothing in it anymore, who's to say what is the right rest frame to use to measure it? But if you just insist on somehow continuing the rest frame that we have now, defined by all the matter in the universe, into the cosmological future, with respect to that frame, a photon, according to all the equations that we know about now, will just get redshifted forever. There's no limit at all. Oh, so now I have two questions. Remember, I'm grouping questions together that I think are at least connected, not necessarily the same, but there's a thematic similarity. So Perry Romanowski says, I posted this last month, and while it was listed in the questions answered, it was not answered, so I posted again. So my apologies for this, Perry. I clearly remember answering your question. I'm not quite sure what happened. It must have been mistakenly cut out when I was editing or something like that. But anyway, the irony being the question is about editing. And the question is, if you said something on a previous podcast or video that you no longer agree with, discovered it was wrong or insensitive, do you edit the old content or do you simply correct the record from now and going forward? And the related question is from Piotrek Bzidl, who says, have you ever recorded a podcast episode and decided not to publish it? Or maybe you were requested, asked by your guest to not publish it. In what circumstances would you make such a decision? So both these questions clearly have to do with, ex post facto editing of podcasts. So I think I don't have a policy about this. It hasn't really come up enough times for me to think through all the possible ways this could happen. If I said something that was wrong, I wouldn't correct it. I might, leave a note in the comments or something like that, but I'm not going to go back and edit the audio file. I mean, by the way, editing is very hard for audio podcasts, not just the physical editing of going into Audacity, which is the program I use to do it, but then you have to re-upload. I put all the podcasts on YouTube, even though they're audio only. Some people prefer listening on YouTube. YouTube simply will not let you edit or replace a file at all. The main podcast files can be replaced, but it's a little bit of a pain. So the default is just to keep it there, maybe flag something if I think it was wrong. Certainly if I've changed my mind about something, I'm not going to go back and edit the podcasts. That sounds like work. It's like writing a book. When you write a book and you change your mind afterward, you write another book or you write an article or something like that. Don't go back and correct all the books. Now, if something was insensitive, if something was, truly like out of bounds and insulting or offensive, that either I said or a guest said, I don't know. I've never come across that particular problem before. I might, in that case, because that reflects badly on the rest of the world, not just me. If I'm hurting the feelings of other people, not just making myself look dumb, then I might think about, going back and editing and leaving a flag up there. I mean, I wouldn't sneakily edit it. If I do ever edit or replace an old podcast, I would certainly want to do so with full transparency. To the question of have I ever not published a podcast? No, I have not ever done that. I mean, it would be hard. I was going to say it'd be hard for me to imagine doing that, but I guess it's not hard to imagine. If someone came on who was truly obnoxious and, violated the spirit of the podcast, then maybe I just would not go ahead and not publish it. But I'm the one who is inviting people on, so I try not to invite people like that. Many of the people I invite on I haven't really interacted with before, so it's always possible. If people didn't want their conversation published after we had recorded it, but before I had posted it, then I would not post it. I'm not going to force people to, put up something that they said, even if they don't want it said before. In fact, that's a very general rule. There's no gotchas here on the Mindscape podcast. I want people to be happy with what they said. So if some people said something and want to correct it or just delete a little bit, that has happened. People have said, oh, I said this thing. I realize now I was wrong. Could you edit that out before you post the episode? And that I will do. And I have done, literally only once or twice in 150 episodes, but willing to do that. Yes. Okay, two more questions that are being grouped together. They're about UFOs. Ben Turner asks, actually, they're about Bayesian analysis and UFOs, so that's the best. Ben Turner asks a priority question. Can you please help me frame how to be a good Bayesian with respect to the credences I assign to the possible explanations to the Navy's UFO reports? And someone labeled Naive Bayesian says, taking a Bayesian approach, how would you decide between UFOs being aliens and UFOs not being aliens? What is the bare minimum evidence you would require to change your mind? A blog post, grainy videos, what would it have to be? So to the first question, the being a good Bayesian, being a good Bayesian means you have some prior credences before any new data comes in, and then you update them when new data comes in. So a huge amount of the difference between perfectly sensible people about the whole UFO issue comes into the priors. And Bayesian analysis does not tell you how to make the right priors, even if there is such a thing. People have tried very hard to come up with what it might mean to have the right priors in a very general sense, but no one agrees about that as far as I can tell. So what is your prior that there are intelligent, technologically advanced civilizations on other planets that send rockets to buzz us, right? Send some sort of vehicles to fly around in our atmospheres. My prior for that is very small, and that's where almost all of the leverage comes from for me. The other part is the likelihood function. So given a certain theory, how likely is it that you would see this data? And here, all good Bayesians should agree. It's not like the priors. Everyone, as I said before, as I said in a book once, everyone is entitled to their own to their own priors, but not to their own likelihoods, the likelihood of the data given the theory. So if your theory is not specifically there are aliens that are flying around in UFOs, but your theory is just there are technologically advanced aliens, that's theory number one. Theory number two is there are not. Okay, so those are the two theories we're trying to compare. What is the probability that even if there were not super advanced aliens visiting us here on Earth, that nevertheless there would be reports of fuzzy objects that we see with our eyes or with our instruments and can't explain? To me, the probability of that is just about one. Of course that's going to happen. Of course there's always things just at the edge of what we can see. They're not very clear and our imaginations run wild. So the data that has another fuzzy picture or another fuzzy video of something does not move me very much at all. Plus the fact that, that is, I think it's something that everyone should have. The difference in priors comes from the fact that, to me, it is entirely implausible that if there were intelligent aliens, they would fly all the way here to visit us here on Earth. Okay, so number one, that's already a lot. Like, how do they know that we would just be becoming technologically advanced right now? Number two, they would buzz us in the atmosphere in small spaceships that tried in some sense to remain hidden from us, but failed. Right? So they have enough technology to fly interstellar distances, to zoom around, stay mostly hidden from us, but not advanced technology enough to stay completely hidden from us, or not enough common sense to do that. That just makes absolutely no sense to me. That is a completely crazy theory in my mind. So I don't give it zero credence, but I give it very, very small credence. Whereas people overinterpreting grainy photographs and videos, that I give very, very high credence to. So to naive Bayesian's questions, what would it take to change my mind? Let me sort of re-answer the previous question as a way of answering this one. To me, it's very much like evidence for the existence of God, right? There are things that religious believers take as evidence for the existence of God. In my mind, if I try to be a good Bayesian and say, what would the evidence be if God really exists? If there existed an omnipotent being that really cared about us, omnibenevolent, loving human beings, that would be very, very, very obvious in my mind. God would not be hiding. God would not be difficult to discern. God would not allow people to fight and kill in his name and misunderstand what he said. It'd be absolutely trivial for God to make himself perfectly 100% manifest, right? You can always, after the fact, come up with justifications for why God doesn't do that. But that's not what a good Bayesian does. The good Bayesian is supposed to say ahead of time, what would your expectations be, and update on the basis of the data there. So you can always come up after the fact with reasons why aliens might come around and visit us, but remain hidden, but fail to remain perfectly hidden. But it's not at all what I would expect. The evidence that I would expect, if it were really true, would be the aliens would just come down and say hi, or they would remain hidden. Those are the two obvious things. This weird in-between thing is extremely unlikely. So the minimum evidence that we require to change my mind, I'm not sure what the absolute minimum would be. No amount of grainy videos will do it. Let's put it that way. I think something much more direct, something that cannot be easily explained away. I mean, by the way, if you're into this thing, just go on YouTube and look for people who've done a really thorough job in explaining how all of these videos can be very, very easily explained without using any aliens or super high-tech things whatsoever, okay? I mean, there's much more down-to-earth explanations for this stuff. Dan O'Neill says, are there major discoveries that you think would have been made by the superconducting super collider that are beyond the powers of the Large Hadron Collider? What justification might be offered now for building a collider more powerful than the LHC? So the superconducting super collider, which was canceled back in the 90s, would have been higher energy and I think also higher luminosity than the Large Hadron Collider. I'm not sure about the luminosity thing. Luminosity is how many collisions per second, but it certainly would have been higher energy. So energy is everything when you do this kind of particle physics at colliders, because E equals mc squared, and you want to make high mass particles, you need to have a lot of E so you can get a lot of M. And so therefore, it's absolutely plausible that there are many, many particles that the SSC would have found that the LHC is not, just because the LHC doesn't quite have enough energy to get there. Now, it's also absolutely plausible that there are none, right? There's basically a range of energies that the SSC could have explored, that the LHC has a lot of trouble exploring, and maybe there's a lot of particles there, maybe there aren't. That's the difficulty. We don't know ahead of time what the answer to an experimental test is going to be because we haven't done the experiment yet. That's why people are really, really invested in these precision measurements like the muon experiments that we talked about in a previous podcast, because even if you are able to find something in one of these precision experiments, you generally only measure one number. You don't know exactly what is the underlying mechanism that is creating it. To really understand what's giving you that number, you need to build a bigger particle accelerator. So if these muon experiments that seem to indicate maybe tentatively, possibly, new physics beyond the standard model are verified and turn out to be correct, that would be very strong motivation for building a collider more powerful than the LHC. Kathy Seeger says, what are your favorite places on Earth, and where would you like to travel to in the universe if you'd had an interstellar spaceship at hand? I think these are two separate questions, Kathy. There is a limit in the rules that you're only supposed to ask one question, but somehow I forgot to edit this, and I just asked them both out loud, so let me give you a stab. The favorite places on Earth question is a weird one, actually. I mean, it's a very obvious, natural question to ask, but it sort of assumes that there's a place you'd rather be than any other place. And I actually like being in different places at different times. You know what I mean? So I love going to Paris, for example, or to Florence, or to Hong Kong, or to Las Vegas, various places around the world. New York City, Boston, San Francisco. I'm a big city guy more than a out in the country guy. But I'm very glad that I don't have to get stuck in any one of those places. So, I like the big cities, the excitement, the experiences, the idea that you can, each night, when you spend a week in a place, you can go to a different kind of experience every night, whether it's food or entertainment or just hanging out with friends or something like that. Those are my favorite kinds of places. If I were able to travel anywhere in the universe, the universe is mostly dangerous and boring, right? Most places in the universe. And the least boring places are the most dangerous ones. It'd be fun to visit, near a black hole and measure the gravitational field and understand whether or not Einstein's theory of general relativity was correct, okay? That's something I would like to do. But I would worry about miscalibrating and falling in, or finding myself in the middle of an accretion disk or something like that. So if I had enough knowledge to be safe about it, I would like to visit close to a black hole and be equipped to do some experiments. David Silbert says, my question concerns probability in an Everettian universe. You address this in the big picture, but mainly from the perspective of how we should think about probability if many worlds is true. Whereas to me, probability is a major issue that many worlds needs to explain. In particular, if a measurement has, say, two possible outcomes, why don't we always observe them as being equally probable? So I almost didn't answer this question because I've answered it many times. There's a blog post that I've written that you can Google called, why probability exists in quantum mechanics or something like that, or why probability is given by the wave function squared, something like that, where I try to answer exactly this question. You mentioned the big picture. Now, maybe that was a typo and you meant to say something deeply hidden, which is my book about quantum mechanics. But if not, if you really meant the big picture, then certainly you should read Something Deeply Hidden, because that's where I explained this in detail. So I'm not going to rehearse every single answer that I have, but let me just give you my one favorite short answer to this, which is that it can't possibly make sense to give equal probability to getting any experimental outcome when there are only two experimental outcomes. Because of what is called, I think David Wallace labeled it, diachronic inconsistency. So, which means that it's not consistent over time, right? So if I have two spins, and apologies for those of you who've heard me give this example before, but if I have start with one spin. I have one spin that is in pointing the x direction, which means that it is a 50-50 chance that if I measure it to be spin up or spin down, I will get spin up or spin down, right? Or at least I can get either one. Let's not presume the probabilities ahead of time. If it's a spin x plus x and I measure it along the z-axis, I could get either spin up or spin down. So I'm going to agree ahead of time that I'm going to do that. I'm going to measure that spin. And if I get spin down, I'm going to get another spin, which is also in the x direction. I'm going to measure it again, okay? If I get spin up for the first spin, I won't. So I measure only one spin if I get spin up the first time, and I measure two spins if I get spin down the first time. What that means is, after measuring the first spin, I have measured one spin, and there's two possible outcomes. It was spin up or spin down, right? So 50-50 chance of getting either one according to this rule. But now I measure two spins on the down branch, right? I say, well, if I measured spin down, I measure the spin again, and I get either up or down for the new spin. So now there's three outcomes. There was either just spin up, or there was spin down and spin up, or spin down and spin down, because I measure two spins if I measure down initially. So if I did those right one after the other, I would say I get three answers, and I should give them all equal probability, 1/3, 1/3, 1/3, okay? That clearly doesn't work, right? Because why is it that the probability you assign to getting spin up changes just because you're measuring a different spin on an entirely different branch of the wave function? It turns out that the only assignment of probabilities that is consistent diachronically, that does not change if you fiddle around with different kinds of experimental apparatuses, is the Born rule, is that the probability is given by the wave function squared. That doesn't mean that it's right, but it's the only one that doesn't have that problem. So you judge about whether it's the right one or not. Jesse Rimler says, I recently watched a Q&A with Noam Chomsky where he was asked to comment on the hard problem of consciousness. Here's my summary of his response. In the 17th century, the hard problem was motion. The great thinkers of the time assumed the universe itself was mechanical. Newton unintentionally showed that this model was hopeless. His theory crucially involved forces that cannot be captured within the mechanical philosophy. Mechanical in this sense is sort of, you can directly see the gear wheels. This is me, Sean, interpolating into the question. But rather than just saying this happens, you actually provide a physical mechanism of things touching each other to explain why it happens. Okay, so back to Jesse's question. Newton's explanation was mathematical, but Newton didn't believe it was an actual explanation. What Newton showed, we're still paraphrasing Chomsky. What Newton showed is that we can understand a theory but not what it means. Thus, the question of motion was abandoned, and science reduced its goals to finding intelligible theories. This was the correct thing to do, and now the same should be done for consciousness. We can find out more about it and develop theories, but we should abandon the idea of solving this current hard problem. My question, says Jesse, is Chomsky's description of the history of science eccentric, or does this square with your understanding, and do you agree with the understanding of abandoning the hard problem of consciousness? Yeah, I would change the wording around in very minor ways, but mostly I think I completely agree with what Chomsky is saying here. I'm not quite sure I would go along with the idea that Newton's theories were not an actual explanation. Newton's theories fit the data, but they did not provide you this mechanical insight, in particular because there's action at a distance, right? The gravitational pull on the Earth from the sun or something like that is just assumed to exist and be instantaneous. There's nothing connecting the sun and the Earth in this particular view. What I would say is not that that doesn't count as an actual explanation, but it doesn't count as the particular type of explanation that you were hoping for in terms of some mechanical gear wheels or whatever. So I wouldn't say that it's not an explanation, just not the kind that you were hoping for ahead of time. And I do think that that is something that scientists have to be open-minded about, that when you ask, well, why is this true? You always have to be open to the possibility. The answer is, well, it's just like that. There's no special kind of mechanism that fills your pre-existing idea of what would count as a solution to the problem. And that's exactly what I think is going on with the hard problem of consciousness. I don't think that there will be a breakthrough where we say, oh yes, now we've solved the hard problem. I think that, so the hard problem of consciousness, sorry, for those who don't know, rather than the easy problems of consciousness, how do we see things? How do we process information? How to react in the world? David Chalmers has isolated the hard problem as the first person experience. Why do I have the feeling that it is like a certain experience to, see the color of red or taste a certain color or something like that? The intrinsically subjective first person part of conscious experience. Explaining that is the hard problem. And the claim in certain circles is that that can't be done with a purely physical view of the world. And I think it's just going to be wrong. I think it's just going to evaporate. It's not that there will be a breakthrough where we say, now this is the answer. It's just that we get better and better at understanding what happens in the brain and in human behavior and in human thought. And we say, that's it. That's what consciousness is. It's all that stuff happening. So that is the extent to which I agree here on Chomsky. I think that the hard problem will evaporate rather than being explained by some brilliant insight. Joy Kolbeck says, what is chirality? Chirality is just handedness, handedness in the sense of right-handed versus left-handed. If you hold up your hands in front of you so that your thumbs are pointing up, the fingers on your right hand are moving in one direction. If instead of up, you point your thumb at yourself, the fingers in your right hand are pointing counterclockwise. The fingers on your left hand are pointing clockwise, right? So that's that difference between right-handed and left-handed. That's what chirality is. It applies in particle physics because there are particles, especially it makes a lot more sense when you talk about massless particles, so that you have particles moving at the speed of light all the time, right? So if a particle moves at the speed of light, you cannot go into its rest frame. It is always moving at the speed of light. And so there is always a well-defined notion of the direction in which it's moving. Count the momentum of the particle as like your thumb, and then the particle can be rotating. It can be rotating around that axis, either clockwise or counterclockwise. So there are left-handed particles and right-handed particles. That's what chirality is. The fact that there can be both left-handed and right-handed particles, and there's the additional interesting fact that in the standard model of particle physics, these particles interact differently. The SU2 part of the weak interactions interacts with the left-handed part of particles, not with the right-handed part. That's a fact about nature that is kind of interesting. Joe Lertola says, I believe you said in your book Something Deeply Hidden that there is a certain weight that's divided between the branches of the many worlds. You said the branching would not continue forever. I found this quite surprising. How do you know this? Well, I don't know it, so I'm sure I didn't say that it would not continue forever. It might not continue forever. So, the branching that is going on, and I mean, let me back up here a little bit, because this is going to come up later in the AMA. There's a very common feature when you try to explain physics using words, but not equations, that you're doing your best to translate very particular, specific, rigorous equations into pre-existing English language vocabulary, okay? And so when you talk about branching and splitting and all this stuff, it's a close approximation to what happens. But what we mean is very specific and definite. It has to do with decoherence and entanglement and the environment and all these extra things that you don't necessarily keep in your intuitive picture when you talk about branching. But the point is that it's possible, I even think it's likely, that a region of space corresponds in quantum mechanics to a finite dimensional Hilbert space. That is to say, there are only a finite number of independent, completely orthogonal quantum states that could possibly say or describe what is happening in this region of space. And you can take that region of space to be our whole observable universe, right? Tens of billions of light years across, a finite dimensional Hilbert space. It's still a big number. The finite dimension is still like 10 to the 10 to the 122 or some big number like that, but it's still finite. So if branching happens all the time, which it does, then it can't happen forever because there's only a finite number of branches you could possibly fit into Hilbert space. What this actually corresponds to dynamically is all of the branches begin to look alike. And that's true because the universe expands, it empties out. Every single branch of the wave function begins to look like empty space. with nothing in it. That's the highest entropy state. And it's a state where all the branches look alike, which means that it doesn't make much sense to talk about them as separate branches anymore. Okay, so it's not that there is like a cessation of the evolution of the universe. It's just there's an equilibration. It's like the ice cube melting into a glass of water. So at some point, it melts all the way, and then it doesn't melt anymore. It's done all the melting it's going to do. That doesn't mean the glass of water disappears into the void. It still exists. Likewise, the universe and the wave function of the universe will still exist, but there's just not going to be anywhere more for it to evolve into a higher entropy state anymore. Alan White says, Alice has an electron. I sure hope that this is the drummer for Yes that is asking these questions. Alan White says, Alice has an electron. When she measures the spin, the universe splits. Bob has an electron that is entangled with Alice's, so she immediately knows its spin as well. Bob is far away, so he will have to wait a long time to learn Alice's result, or he can measure his own spin. However, if he measures the spin, the wave function does not split. I find this very confusing, perhaps because I'm expressing it in words rather than mathematically. See, I told you, the whole words versus math thing would come back up. So, again, I've said this before, but I'll try to say it again because not everyone hears everything I say for some reason or another, and also because saying things slightly different ways is sometimes helpful. The idea of taking the wave function of the universe and describing it as a set of branches is very, very convenient. It is a useful thing for we human beings to do because what we label as different branches don't interact with each other. They act like they're independent, separate worlds, thus the many worlds interpretation. But the universe is the set of all of the branches, okay? And so you need to ask the question, what is the best way of taking the universe, the whole wave function, and dividing it up into branches? And it's not obvious that there's a right way or a wrong way. So in my view, it's up to you whether you say that when Alice measures her spin, Bob, the wave function of the universe instantly splits everywhere, including where Bob is, or you have some patchwork quilt of branches which says that in Alice's future light cone, the wave function of the universe branches, but outside it doesn't. So in that view, Bob doesn't split until Alice's light cone begins to intercept him. So what this means for Bob is, let's take the first point of view. Let's say that when Alice measures her spin, the whole universe instantly, simultaneously splits in some reference frame, and you can pick what reference frame it is. It doesn't matter for any possible observational outcome. So now there are two copies of Bob, right? It's not that there is Bob with one spin. There is a version of Bob on the branch where Alice measured spin up, and a version of Bob on the branch where Alice measured spin down, okay? So as you say, when Bob then measures the spin, the wave function doesn't split. That's true because it's already split, right? There are two different Bobs. They're both measuring a spin, which is guaranteed in each case to give them a definite outcome. So there you go. In the other point of view, where the branching happens with the speed of light but no faster, rather than simultaneously, then, when Alice and Bob measure their respective spins, splitting does happen in both cases. But the different branches get knitted together when their light cones begin to overlap in such a way that where Alice measured up, Bob measured down, and vice versa. So it all works out, but there's a little bit of arbitrariness here in how we divide up the universe into branches. Volaire O says, is there anything you had believed in but completely changed your view on? Oh, I should have grouped this with a later question, but that's okay. Yeah, sure. I mean, obviously, like I used to be very young. I used to be a kid, and I believed all sorts of crazy things. I believed in psychic powers at one point in my life as a child. In university, I believed that you could develop rigorous scientific notions of morality and ethics based on nothing but science. I completely changed my mind on that. In more late in life terms, I believe that the cosmological constant was zero pretty strongly, right? But my belief in that went away because we had data that really changed its mind. In more personal ways, I believed that it was really, really interesting and important to think about all the different ways that the accelerating universe would be caused by something other than a cosmological constant, or so dynamical dark energy or modifying gravity to get rid of dark matter or dark energy. But, you know, in working on those ideas over and over again as a theorist, and then in watching the data come in again and again, favoring the good old-fashioned ideas, you know, I thought I'm not sure that those ideas are wrong, but they're less urgent to me. They seem like less likely to lead to a breakthrough. So I changed my view on that. So yeah, you know, I changed my view about all these things. I've changed my view about the importance of the budget deficit. I used to really be thinking that the federal government should always balance the budget every single year. But I know better than that now. I think that was a very naive economic point of view. Not to say that you should let the budget deficit grow without any bound whatsoever, but it's very natural to have a deficit, to have a small amount of inflation, to let that encourage growth, et cetera. You know, pay back some of the debt when the economy is growing. There's a whole much more sophisticated view that people should have, and that I had than what I had, is what I'm trying to say. Gillis15 says, I live in Denver, but am now a native New Mexican, so I'm curious about how you ended up being an external professor at the Santa Fe Institute, and have you visited the Los Alamos National Lab? And regarding New Mexican food, red or green? So those of you who've been to New Mexico know the state official question is red or green, and it corresponds to the color of chili that you want on your food when you're eating it. You get red chili or green chili. I'm definitely a red chili guy. That's a very easy question. Sometimes I'll feel adventurous and go for the Christmas option, which is half red and half green, but I can't imagine just straight green unless it was a very specific dish that called exactly for that. I've not visited Los Alamos. No, I don't. At least I don't think so. Certainly not for many, many years. I don't think I ever have. I'm pretty sure. For Santa Fe, you know, it was always a natural fit for me, but one that never just quite came to fruition. You know, back when I was in graduate school, I think that was when SFI was founded, or at least it was founded not long before I entered graduate school. And, you know, I had on the bookshelf that I was gradually accumulating these big red volumes of conference proceedings from conferences at Santa Fe about quantum cosmology and complexity and entropy and information that I thought were all fascinating and interesting. But just in the circles that I moved in as a professional cosmologist and gravitational theorist, that really didn't overlap very much with what Santa Fe did. Once I became interested in entropy and the arrow of time, there was a more natural connection, and so I went to a couple of workshops there at SFI, and I loved it, and they at least tolerated me or enjoyed having me there, so they invited me to be an external professor. That's basically it. You know, I talked to them, we interacted, it all went well. That's just about it. Chris Dillon says, how likely do you think it is that humans will one day develop a technology that can be used as Laplace's demon? Will we ever be able to reconstruct a historical event down to the finest detail? No. Zero likely. 0.00001% likelihood. Because it's gone. Because the data, the information that was in any particular historical event, some of that was in the form of photons being radiated away into outer space. And there's no way we can catch those photons. They're moving away from us at the speed of light. Furthermore, we can't build something as delicate enough to measure all the photons or atoms in anything, in any macroscopic thing. In a tiny molecule we can, but once you get to a big macroscopic scale, it's just impossible. You don't have the resolution. Literally, you don't have the resolution because if you used high enough energy photons, right, short enough wavelength to give you resolution on all the microscopic locations of the particles, you would also destroy the thing you're looking at, and you would not be able to measure the whole thing. So that is completely 100% implausible to build or even come close to building Laplace's demon, which is why it is absolutely just a thought experiment, nothing more than that. Casey Mahone says, you've totally persuaded me on many philosophical ideas, but there's one I just can't side with you on. That's the principle of sufficient reason. In my mind, if there are two possible ways for the universe to be, there's got to be some kind of explanation for why it is one way rather than the other. Could you go a bit deeper in how you justify the existence of brute facts in the world? Well, you know, I think that the burden of proof is on your side, Casey, not on my side. You know, you're saying there has got to be some kind of explanation for why the world is one way or the other. Why? Why does there have to be some kind of explanation? I mean, I can understand that you would be interested in getting some kind of explanation, but there's no logical reason why there has to be. To be more substantive about it, there's the whole philosophical thought experiment of possible worlds, right? We think about different possible ways the world can be. David Lewis was the philosopher who was the master of this, but it's an absolutely central idea for any human being, possible worlds. Even if they don't use that vocabulary, whenever you say, I put on the wrong socks this morning because I didn't have my coffee yet. What you're imagining in your mind is that there's another possible world in which you did have your coffee and you did not put on the wrong socks, right? You're comparing what actually happened to a different possible world. And I think that as far as physics or even physical events are concerned, it is very easy and straightforward to imagine other possible worlds. And so what picks out this world as the best, as the right one, right? Given that there's more than one possible world, the fact that we live in one rather than the other is going to have to come down to a brute fact, right? I could be wrong about that. I mean, that's trying to be logically reasonable, but that's what goes into my mind when I think about this. And I'm not afraid of brute facts. These questions about why things are eventually going to bottom out somewhere. I can't see how it could be any other way. Ken Wolf says, have you had any exposure to East Asian pop culture, whether it's manga, anime, Hong Kong cinema, or anything else? And if so, is there anything you found particularly memorable? Not really. No, honestly, I've had the usual amount of exposure that a typical American of my age and socioeconomic status would have. So certainly I grew up watching Godzilla movies and Japanese TV shows from Ultraman to Speed Racer. These days, later in life, I've watched the Studio Ghibli movies, Hong Kong cinema. I'm married to someone who has a black belt in jiu-jitsu, so there's a lot of Jackie Chan and Chow Yun-fat movies in our rotation. But I'm not in any sense an expert, nor is it in any sense central to my pop culture diet in any way. I try to keep my pop culture diet somewhat eclectic and diverse, and so East Asian pop culture is part of it, but it's not something that I'm in any sense an expert in. Tim Kennedy says, I was very interested in your recent podcast with Henry Farrell and the concept of epistemocracy. What are your own thoughts on weighting voting impact with some sort of coefficient, like contribution to budget or some other relevant metric that might govern how much say someone should have in the running of things? I think that's a terrible idea. Sorry, Tim, if you like this idea, I'm not sure, but it's just incredibly rife for abuse, right? Once you say that not everyone's vote counts equally, but rather some votes are more important than others, someone's going to have to decide what the importance is, and the people making those decisions, guess what? They're going to weight things so that their votes count more. That's just always going to happen. So I think it's just opening yourself up for all sorts of abuse. In particular, the idea of weighting votes by contribution to budget is more or less the opposite of what I would do. We should weight the votes negatively for people who have a large contribution to the budget, or we should push them down to zero because they influence the process in other ways, right? Rich people have a hugely outsized impact on the current way the government goes. To also give them more oomph to their votes would be just bringing coals to Newcastle, as it were. And besides that, I think, so those are just all practical considerations. There's also a philosophical consideration. What Henry and I talked about is the idea that democracy does a better job than you might think at solving problems. Like if you have a bunch of people in a room and they're faced with a task and they organize themselves along different lines, whether it's an autocracy or market system or democracy, Henry's point is that a democracy is better than you might have thought at solving problems. But it's not the point. That's just a bonus. That's not why we have democracy. We have democracy because we have the idea that all people are created equal, or should be treated as if they are. Every person has a voice and has a right to have something to say in how the country is run, if they want to have such a voice. So that's, for me, the reason why everyone gets an equal vote, not because I think that they're smarter or better or contributing more or anything like that. That's not just not a consideration when you decide how to count votes. Jason says, is the black hole information paradox really a paradox at all in all interpretations of quantum mechanics? Spontaneous collapse theories as I understand them, are not fundamentally information conserving. How is Hawking radiation different from any other seemingly random quantum event? I'm including this in the list of questions, even though my answer is I have no idea. I do not know what someone who believed in spontaneous collapse theories would say about Hawking radiation. I'm not someone who follows spontaneous collapse theories, and I'll elaborate on that later in the AMA. But that is an absolutely interesting question, which is why I'm saying it out loud anyway. A lot of people in the area of fundamental physics, particle physics, cosmology, string theory, gravity, all those things are more or less implicit Everettians, even if they don't care about the foundations of quantum mechanics, so they wouldn't necessarily characterize themselves in that way. Deep down, that's what they are. Not everybody. Tom Banks, for example, is a famous counterexample. I think he's basically close to an epistemic person when it comes to quantum mechanics. New and improved Copenhagenist in some kind of way. But most people are basically Everettians, and that's why it makes sense to them to say, in the absence of some measurement process, evolution should be unitary. You're completely correct if you don't think evolution should be unitary at all, even if there's not a measurement going on, then your attitude toward the information puzzle might be very, very different. I'm not sure what it would be. That is my point, because I haven't actually followed that stuff. I should also say one more thing, which is that the reason why I don't know might very well be that that's just not the kind of thing that advocates of spontaneous collapse theories spend their time thinking about. This is one of the things that I try to emphasize, but I think is underappreciated, which is that all of the non-Everettian approaches to foundations of quantum mechanics, whether it's spontaneous collapse, hidden variables, epistemic theories, etc., it's a community that thinks very, very hard about non-relativistic quantum mechanics, about quantum mechanics circa 1930. They're not thinking about quantum field theory, quantum gravity, string theory, black holes, or anything like that. And there's a reason why, because all of that stuff doesn't fit in very well with these alternative theories of quantum mechanics. They go to great lengths to make a theory of an electron in an atom, but making a theory of space-time itself is just a very, very different thing, and you have to start from scratch in any of these theories. This is part of the motivation for my Mad Dog Everettian approach, because Everettian quantum mechanics is the one approach that says if you give me the Hamiltonian, as we say, the energy of a quantum system, everything else is supposed to be emergent. You don't need to do any more work in putting more ontology in or more dynamical rules in. All of the other approaches involve either new elements of reality or new dynamical rules or whatever, okay? So once you have a different system, you go from a single particle to a field to space-time, you have to reinvent what all those new rules are. And in Everettian quantum mechanics, you don't. There's something you do need to do, which is to show where all the structure in the world comes from, why there are tables and chairs and branches and things like that, and that's what I and others are trying to do. Chris Rogers says, I just bumped into a TV editor I know who tells me he's working on a documentary series about the universe. Apparently, there's an episode all about the Big Bang and in part what happened before the Big Bang. I asked what that could possibly mean, and he said apparently they have some new data that allows us to understand the universe before the Big Bang. I'm English, so I just nodded politely. This can't be right, though, can it? It depends on the referent to the word this in this sentence. Chris, I'm a big believer that there might very well have been a universe before the Big Bang. My first trade book, called From Eternity to Here, outlines exactly such a theory of my own. But what I bet with pretty good credence is that they're talking about Roger Penrose's conformal cyclic cosmology models. Penrose, former Mindscape guest, has proposed a model of cosmology where once the universe empties out and there's nothing but empty space, a miracle occurs, and it suddenly becomes a hot, dense, expanding Big Bang kind of universe. And what he claims is that evaporating black holes in the previous universe can leave an imprint on the cosmic microwave background in the next universe. And furthermore, he and some collaborators believe that they've seen these imprints of these evaporating black holes. So what I can tell, and that's probably what they're referring to when he says some new data that allows us to understand the universe before the Big Bang. But essentially nobody else believes this other than Penrose and his collaborators. There's plenty of working cosmologists who would be very, very happy to find evidence of a pre-existing era of the existence of the universe in the cosmic microwave background. None of them believe the claims that are being made by Penrose and his collaborators that they found such evidence. And of course, even though Penrose is a co-author on the paper and believes and accepts these claims that there is such evidence, he's not the one who did the analysis, right? I mean, he's one of the world's great mathematical physicists, but he is not a cosmic microwave background data analyst. That is a different skill set. He needs to trust the people he's working with, and the other experts in the field don't trust them. I'm not an expert in that field either, so I'm just going to go with the majority in this particular point of view. Anders Hector says, it'd be very interesting to hear you describe the principle of conservation of information without using the word information. Sure, that's very easy to do. I've done it many times. Principle of conservation of information is just the idea that the state of the universe at any one point in time, plus the laws of physics, determines the state of the universe at all previous times and all subsequent times. That's it. That's what the conservation is. The use of the word information is just a translation of the term the state of the universe into something a little bit more graspable and quantitative. ACAC, I'm not sure if that's an acronym or it's ACAC, but that person says, on your 70th episode of Mindscape with Professor Katie Mack, you mentioned that you like the term smooth tension for dark energy. I was surprised to hear that and thought it was kind of cool because Professor Edward Copeland also mentioned that he likes that term smooth tension. I'm pretty sure you were on Brady Haran's YouTube channel, 60 Symbols, where Professor Copeland is often featured. I have to ask, did you ever get to hang out with Brady's crowd? Did you stay in touch? Do you have any cool stories? And is there a secret smooth tension movement in the physics community? Yes, the term smooth tension goes back to a review article on dark energy and the accelerating universe that I wrote in the early 2000s, where I pointed out something that many other people have pointed out, which is that dark energy is not a very good name for dark energy. I mean, dark matter is not a great name for dark matter. It is matter, though, the dark matter, rather than being radiation or something else. Okay, so that's at least somewhat informative. And it is dark, but the more important thing about dark matter is that it's transparent, right? It's invisible. So calling it invisible matter would have been more accurate, but it would sound spookier, so maybe dark matter is fine. Dark energy, likewise, it doesn't glow, so it is dark, technically speaking, but again, it's invisible. That's the important thing, not the fact that it is not glowing. And yes, technically it's energy, but everything is energy. Everything has energy. Matter has energy. Radiation has energy. So you're just not conveying a lot of information when you say dark energy. The important thing about dark energy, besides the fact that it's invisible, there's two important facts. One is that it is everywhere, right? It is spread smoothly throughout the universe. It does not clump into galaxies and stars, so it is smooth. And the other important feature is that it has a negative pressure. Rather than pushing, it pulls. If you had a bottle of dark energy, it would be like having springs inside the bottle pulling on the edges, pulling them together, a kind of tension. The gravitational effect of the dark energy is to push the universe apart, but the energy itself has this negative pressure, aka tension. So I proposed, half jokingly, that it would be more accurate to call it smooth tension. Okay, it was not ever of the misguided opinion that it would catch on, other than as a half-hearted joke. It is more accurate than dark energy, but the labels that we put on things in science are not necessarily chosen for their accuracy. Whichever is the first one to stick, sticks, and then you're stuck with it, right? Quantum mechanics is not a great name. Relativity is not a great name, but those names have stuck. So yes, Ed is a friend of mine, and he read the article and he liked it, so he's been another proponent of smooth tension. But I don't really hang out with those folks. They're in a different country. Brady Haran lives very close to Ed Copeland and all the other people who appear on 60 Symbols. I'm not going to start listing them because I'm going to leave some out and then insult them. But it's a great YouTube channel. If you haven't watched it at all, I always call it 60 Seconds for obvious reasons, but it's called 60 Symbols, and they do a great job talking about different aspects of physics. I've talked about quantum mechanics and the arrow of time there. Randall Newman says, can you talk about how you go about deciding on what problems to solve, and more importantly, what your research process is like. What tools do you use? How do you work out proofs and experiments? How do you collaborate with others? Actually, let me combine this with a question from Umberto Nani, who says, may you please comment on how you select an idea to pursue it to be the matter of a paper, an article? How do you decide the worthiness of something as to decide to work on it? So both questions are about, deciding what problems to work on as a scientist and then the process by which you're doing it. If you want more details on this, I did, again, write blog posts. I wrote a series of 3 blog posts a few years ago called Anatomy of a Paper, Part 1, Part 2, Part 3, where I took a paper that I had recently written with Lottie Ackerman and Mark Wise, and I explained where the idea came from, how we worked it out, how we collaborated, all those things. And so it was a nice paper about what the microwave background would look at if the universe were anisotropic on very large scales. So if it had accelerated during inflation, for example, at different rates in different directions. That's a kind of overall cosmic anisotropy. And so we worked out from the idea, what the paper would look like, and we published it. So if you want some details there, it'll be longer than the following answer. But these are good questions because as a scientist, once you've forgotten about getting your job and getting your grant money and all that stuff, you're always faced with the fundamental issue of what to work on. And as a theoretical physicist, especially where you don't have a giant laboratory, you don't have a lot of superstructure built around you, you might think, well, I could work on a different thing after every paper is done. But of course, that's not completely true because you have areas of expertise. You have questions you have cared about in recent times. You have students and postdocs who you're working with, other collaborators who you might be working with who have their own interests. So there's sort of a very natural way to build on what you've already done, right? That's the most easy thing in the world as a working scientist, is just to do a little bit more on what you've done outside. But otherwise, the way that you come up with a problem, there's no algorithm, right? I mean, there's no simple answer to that question. You can either take a question, an issue that has existed for a while, and you're just chewing over it, right? Why is the past different from the future? Or, what happened at the Big Bang? Or how does gravity work really? Where does space-time, like all these big questions, and you can just sit and think about them in some idealized sense. Mostly it doesn't happen like that. Mostly what you're doing is you're interacting. Mostly the ideas for papers come from not sitting by yourself in your ivory tower, but from reading other people's papers, talking to people one-on-one or one-on-several, going to talks that other people give, reading papers that appear in the archive, things like that. And so you are constantly bombarded by other people's ideas, and different scientists will have different levels of openness to those ideas, right? I mean, some people are just very focused on their current problem and couldn't really care less. Other people are, always interested in digging into what other people are working on and therefore thinking about them in new ways. Sometimes people are dramatic in how they change what they're working on. Jeffrey West is a great example of that. He was one of the first Mindscape guests, where he was originally doing work on particle physics, supersymmetry, phenomenology, as we call it, inventing new models of other particles. And when the superconducting super collider got canceled, as we just said, he said, nope, I don't want to do this particle physics stuff anymore. I'm going to switch fields entirely. And he became a complex systems researcher. And so he now writes books on scale and cities and biology and things like that. So, there's no algorithm. You have to chase what you think is interesting. Think about puzzles. There's a huge number of puzzles out there in the universe that we don't know the answer to. The art form is to formulate a puzzle that is answerable, or at least progress can be made on it in some way. To talk about Randall's question about what tools, what proofs, etc. I'm a theorist. I use pen and paper, pencil and paper. I use pens more than pencils. That doesn't mean I don't make mistakes. That just means I cross them out. These days, sometimes I use the iPad Pro and an Apple Pencil. And so it's all scribbling down ideas, equations, working them out. A lot of my physics papers are in collaboration with graduate students. So that depends a lot. I mean, very often I have an idea because I'm the old head, right? I've been around for a while. I would say it'd be interesting to think about this, go off and think about it. And we try to see whether with, conversation, can we come up with a particular angle on the question that is work onable, publishable, able to write something. There's constantly a question in the academic community. What is the least publishable unit? You make some progress, you learn something. Is it just, something that is amusing to you? Do you write it up but then just share it as notes on your webpage? Or is it worth actually publishing as a paper? These are ongoing conversations, and it's not very clear. So in many ways, it's something you learn by doing, right? You can't actually be handed the right answer to this. You have to actually take things up and decide for yourself where it's going. DLP says, is it accurate to think of observing a quantum state as merely becoming entangled with that state? It's close, but I wouldn't put it exactly that way. It depends on what you mean by observe, obviously, okay? In the traditional Copenhagen-esque way of thinking about things, the thing doing the observing is ultimately a person, right? A conscious agent. They might use some apparatus or whatever, but the observation itself adheres in the act of the agent doing the observing, and that's why the word observing made sense. John von Neumann extended the formalism a little bit so that not only did small quantum systems, like an electron with a spin or something like that, have a wave function, but he allowed the apparatus, the measuring apparatus, to have a wave function also. He did not allow the observer to have a wave function, though. Everett was the one who really pushed the idea that even the observer should be part of the wave function of the universe. So once you get to the Everettian way of thinking about things, there's no special role of observing. The observer is just another quantum system with a lot of degrees of freedom. So we change our focus from the word observing to the word decohering. That's what really matters in Everettian quantum mechanics. And decohering comes from the idea that there are quantum systems that are typically microscopic, but they're in superpositions of different possibilities. And there's also an environment that we don't keep track of. Many, many degrees of freedom, particles flying around in the air, in the photon bath in which we're all embedded, stuff like that. And so the branching of the wave function of the universe to an Everettian, that's what matters. And that happens when decoherence occurs. And decoherence is the tiny quantum system becoming entangled with the environment. So in that more modern framework, yes, entanglement is completely central, but it's not entanglement with the observer that matters. It's entanglement with the environment. The observer is already entangled with the environment, so they go along for the ride in a very trivial way. All right, two questions I'm going to group together, which is really, really weird because, I've literally never had questions about this topic before. Now I got two of them. They're both about what is called the master equation. So Jeff asks a priority question. I'd be grateful if you could discuss the master equation in quantum and classical physics without shying too much away from the mathematics of it. And David Wright says, I was reading one of Steven Weinberg's essays on quantum mechanics and his view on some of its remaining issues. And he mentioned that the wave equation is actually a special case of the more general Lindblad master equation. The Lindbladian models the time evolution of non-equilibrium open systems and would seem to be very useful for dealing with processes above the fundamental scale. I'm curious why the Lindbladian is not more widely referenced in the scientific literature. So there are two things going on here. There's the idea of what is called the master equation, which makes it sound a little bit more important than it is. And master equations apply whenever you have something that has a probability attached to it. Okay, so if you have some process, whether it's flipping a coin or the state of a spin or something like that, a spin is being buffeted by thermal fluctuations around it. And the master equation just shows you how a certain probability distribution evolves over time. Typically, a master equation is just linear. So what that means is you start with the probability distribution for different possible states of the system, and you act a simple linear matrix on it to get you the rate of change of that probability distribution, and you call that the master equation. And it appears, as Jeff says, both in quantum and classical physics. The Lindblad equation is a specific example of that kind of thing, but it's a little bit more general, as David said. It allows it's an equation for the density matrix, which is a sort of quantum mechanical generalization of the probability distribution of a classical system. And it's not strictly just multiplying a matrix by the density matrix. That's why it's a slight generalization. So this is obviously a very powerful and important idea. There's plenty of circumstances in which you have a probability distribution. You want to ask how it evolves with time. But there's a huge, huge problem with these equations, which is that they often don't work. These equations, the master equation, the Lindblad equation, etc., work in very specific circumstances, and in other circumstances, they just don't work. Like the Schrödinger equation always works, but it only works to the extent that you know the complete quantum system. What you're trying to do with the master equation is to ignore some parts of the quantum system and focus in on some other parts. That's why you have an open system, right? So you have a system here which is not isolated from the world. There's other parts of the world that could bump into it and affect it in some way, but you're trying to say, what can I say about the evolution of this system without specifying what the rest of the world is doing? So you instantly see why that's difficult, right? I mean, you can say, here I am in my office making this recording of the AMA. What am I going to do next? What's going to happen to me? How will I evolve? And that's a perfectly reasonable question. And if the office was a closed system, in principle, I could answer it. But the office is not a closed system. Someone could walk in the door. The phone could ring. A meteorite could come down and smash into the house, right? Many different things could happen, all of which would have a dramatic effect on how I would evolve in the future, and none of which are sensibly modelable in any easy way. Who knows whether a meteorite's going to hit the house or not? So typically, the restricted circumstances under which the Lindblad equation makes sense is when you say, well, specifically, even though I don't know exactly what the environment is doing, let's just say it's a uniform, homogeneous thermal bath. Okay, so there's no meteorites out there. There's just the atmosphere at some temperature or something like that. Then you can do a pretty good job. But really, if you really want to get an accurate description of what's going to happen in my office, you have to include the possibilities that unanticipated things are going to happen from the outside world. And that's why you need a more general framework. Lewis B. says, I've invented my own interpretation of quantum mechanics called the one world interpretation of quantum mechanics. It's exactly the same as many worlds, except all but one world collapses and doesn't exist. Is there any material difference between my new one world interpretation and the Copenhagen interpretation? Put another way, is the only difference between Copenhagen and many worlds the claim that other worlds are real? Well, you don't yet have, Lewis, an interpretation of quantum mechanics. Sorry about that. You can't just say all but one world collapses and doesn't exist. You have to say which worlds collapse. Is it random? Is it random in some measure? Who chooses? And more importantly, you have to say when the collapse happens. Does the collapse happens? Do collapses happen when there's a certain physical criterion that is reached? Or is it just stochastic? Does it happen occasionally? So these are all different kinds of ways that you can make something like that happen. And guess what? They've all been explored. So something like Roger Penrose's attempt to interpret quantum mechanics is a objective collapse model where the collapse happens when a certain physical threshold is reached, when superpositions become more than the Planck scale or something like that. Whereas things like the GRW theory are spontaneous collapses. So again, they only have one world, but there's no special threshold that needs to be reached for a wave function to collapse. It's just that wave functions collapse every so often. So they're different theories, right? But also, most importantly, none of them are in any sense many worlds. The entire point of many worlds is that the Schrödinger equation is always obeyed, right? The Schrödinger equation says that more than one world will come into existence. So any other theory violates the Schrödinger equation, modifies it, alters it in some way. That's fine. You know, if you don't want all the many worlds, then by all means invent a new rule where you modify the Schrödinger equation. But this is physics. You got to tell me exactly what that modification is, very, very quantitatively and rigorously and objectively. Until then, you don't quite have an interpretation of quantum mechanics. Rodrigo Nader says, do you see emergence as a human concept or fundamental in nature? Is it a consequence of our reality being shaped by patterns? I think emergence is a fundamental thing. Well, I shouldn't use the word fundamental there because often emergence is contrasted with fundamentality. There are fundamental parts of nature and there are emergent parts. But emergence, I think, is built into the fabric of nature rather than just being a human concept. I think it's actually an easy mistake to make, or at least an easy confusion to draw, because we often say that emergent phenomena are ones where you can say something about the phenomenon without knowing all of the microscopic details, right? You can say something about cream and coffee mixing together without knowing everything there is to know about the individual molecules inside. And that makes it sound like it's just a convenience for human beings. We don't know everything, so we say whatever we can. But the generic situation, if you didn't have specific laws of physics, if you had general laws of physics that were not embedded in a certain way, in a certain framework of locality and microscopic interactions and things like that, there wouldn't be anything you could say from the low information point of view about the behavior of the system. It would be necessary to know all of the details. Sometimes that is true in nature, right? Some things in nature you would need to know all the details. Like you don't know when a particular volcano is going to erupt ahead of time just by looking at it and knowing its macroscopic features. You would need to know all sorts of microscopic features to predict that exactly, and you never will. But there are other cases, like the orbit of the Earth around the Sun, where you don't need to know all the microscopic features of all the particular atoms and molecules in the Earth. You just need to know its center of mass. So it is a feature of our laws of physics that it allows these emergent behaviors in ways that human beings have observational access to the data you need. Even though it's incomplete data, it's macroscopic rather than microscopic, it's still enough to make reasonable predictions. And that's a nice feature of the laws of nature that didn't have to be there. Okay, I'm going to group two questions together. One is from Abdul Afzal, who says, on one of your Reddit Q&As, you mentioned that Tim Maudlin came close to changing your mind on Platonism about math. I was curious to know his line of reasoning was, and did you ultimately not change your mind in the end? And then Michael Edelman said, have any of your guests strongly influenced or changed your thinking on a particular topic as a result of the conversation you had? So maybe this is a little bit of a stretch, gluing these two questions together, but the general theme of changing my mind is once again here. For Tim Maudlin, I'm going to be honest here, more honest than I should be, and say I don't remember specifically what it was that Tim said because not that I haven't thought a lot about Platonism about math, but since talking to Tim about it, I've talked to other people about it, and there are arguments that are in my mind, and they have a certain salience, but I don't remember where they came from. I don't remember who told me which argument, so I can't say exactly what it was in that particular conversation. The thing that is, I'm still up in the air about this. I'm not a Platonist about math, but I'm not strongly anti-Platonist. There might be some version of Platonism that I'd be willing to sign on to. I just haven't sort of settled my personal beliefs about this. I think that one of the things that gets me thinking that you need to take something Platonistic into consideration is the idea of counterfactuals. We talked earlier on about possible worlds, and this is something that is very important, a concept that you need to do physics or science or anything else. You talk about other possible worlds. But if you're not Platonistic, if you don't think that math exists out there as a real thing, maybe what you want to think, these are a whole bunch of ideas that are mixed up together, but there's this Humean idea that all that exists is the universe, right? And sort of that's where I want to be. That's my natural happy place for me. All that exists is the universe, and everything else is, we have a way of talking about it, including math. But if all that exists is the actual universe, how can you talk about other universes? That's hard. Like when you talk about other universes, you usually attribute to them the same laws of physics and the same mathematical structure, right? But if those laws of physics and mathematical structures don't have independent existence from our universe, what gives you the right to do that? How do you know how to carry over the physics and math from one universe to another? I don't think that this is a really killer argument, to be honest. I think that there are ways to justify doing that, but my own understanding of it is not quite sophisticated enough to really promise you that I have the right answer where it comes to that. I'm still thinking about that. And for Michael's question, have any guests on Mindscape? Tim has not been a guest on Mindscape, but have any other guests changed my mind about something? Usually not. It's not the standard thing. Sometimes I have a guest on who's talking about something that I knew nothing about, right? So when Rachel Loudon is talking about the history of world cuisine, she didn't change my mind, but because I didn't have many strong opinions about it, but I learned a lot. So that's a kind of changing your mind. Maybe Joe Walston, who talked about urbanization and its relationship to the environment, was something where I thought maybe I knew a little bit, but I was wrong, and I definitely changed my mind about that. But I don't think I've had any epiphanies that really made me completely change my mind. The talk that I did with Ned Hall actually touched on these issues of Humeanism and Platonism and so forth. And so that is part of the conversations that are all mixed up in my brain about those things. So maybe that had an impact also. Jan Smit asks a priority question, which is a multi-part question, but I'll grant it this one time. The question is, what do you think of Sabine Hossenfelder? She says the many worlds interpretation does not solve the measurement problem, and she finds string theory not interesting. It has made some contributions to mathematics, but even so, this would have nothing to do with string theory as an approach to a unified theory. So I will interpret your question as, what do I think of these particular opinions that Sabine, or beliefs or positions that Sabine holds? I don't want to talk about what I think of individual people. Sabine is a friend of mine. She blurbed one of my books. I think she did, or I blurbed one of her books. I don't remember. But, she's a real physicist, unlike some commentators on the internet about physics things. Sabine is an actual practicing real physicist and deserves to be listened to. We also disagree about a bunch of things, just like I disagree with Lee Smolin about a bunch of things, or David Albert about a bunch of things. So she says the many worlds interpretation does not solve the measurement problem. I disagree. I don't know exactly what she says about it, to be honest. But I've written a whole bunch about the many worlds interpretation and why I do think it solves the measurement problem. So you can certainly read that. She finds string theory not interesting. That's great. That's completely allowed. I'm definitely one who thinks that when it comes to unproven ideas in theoretical physics, we should have a pluralism of different approaches, diverse approaches. As I talked about in another context with Musa Al-Gharbi some time ago, I believe in intellectual diversity when it comes to that. So if some physicists think string theory is not interesting, that's great. Others do think it's interesting. That's also great, right? We don't know yet, I think, is my particular attitude. A lot of the debate and discussion about something like string theory comes down to, will it be correct? String theory might be correct. It might actually be that what we think of as electrons and neutrinos and quarks are really little loops of vibrating string. In that case, I certainly think that string theory is interesting, but we don't know, right? It might not be the case that that's true. So it's just a judgment call. It's not really something that we can prove one way or the other, and different people's judgments will differ. Anders says, do we think that black holes erase information about baryon and lepton number? Yes, we do. So if you make a black hole out of a bunch of baryons, for example, and then you let it Hawking evaporate, typically we think that it will mostly evaporate into photons. A few gravitational waves or neutrinos. In rare cases, it would emit a proton or an electron or an antiproton or an anti-electron. But when it's emitting photons, those photons have zero baryon number. And when it emits baryons, which it will occasionally but rarely do, it's 50-50, we think, whether it emits a baryon or an antibaryon. So the general thought is that baryon and lepton number are not conserved in black hole information, which it is also thought, and again, we don't know these things for sure, but the thought is this is a generic feature of quantum gravity, not just a particular feature of black hole evaporation, but the general feature is that gravity doesn't know the difference between baryons and antibaryons, okay? Gravity knows how much energy you have or how much mass you have. And if you believe in the basic principles of quantum field theory, baryons and antibaryons have exactly the same mass. So they couple to gravity in exactly the same way, so we wouldn't expect gravity to care about whether or not it was interacting with a baryon or a lepton, or a baryon or an antibaryon, I should say. So generically, we expect gravitational interactions to not conserve those quantities. We have never observed it, though. These are very, very weak hypothetical effects. Edward A. Morris says, is it theoretically possible to have two particles with the exact opposite wave functions so that they perfectly cancel each other out and disappear like sound waves in noise-canceling headphones? So yes and no. I mean, strictly speaking, the answer to that is no, because what you're doing is you're thinking about wave functions too literally like waves. Wave functions are not waves. The difference is that every particle doesn't have its own wave function, right? There is only one wave function for all the sets of particles in the universe. So you can't have the wave function of particle 1 and the wave function of particle 2 interfere with each other, because interference happens only between two different instances of the same thing. But what you can have, and what you might be thinking of, is two different contributions to the wave function of the same particle can interfere with each other. Indeed, that's exactly what happens in the double slit experiment. In the double slit experiment, you get an interference pattern, which can be thought of as one part of the wave function of the particle interfering with another part of the wave function of the same particle. Ron Greiber says, what would Laplace's demon think about the three-body problem? More directly, in a deterministic universe, how should we think about chaos and randomness that can't be backward resolved or forward predicted? Laplace's demon has no trouble whatsoever with the three-body problem or the Avogadro's number of bodies problem, because Laplace's demon, by construction, has perfect information about the universe and perfect ability to calculate. Now, as we already discussed earlier in the AMA, no real computer or person ever has that. So for real things in the universe, when you have chaotic behavior, you cannot predict exactly what's going to happen on sufficiently long time scales, but Laplace's demon doesn't exist. Laplace's demon is a thought experiment with perfect information. So I think that's a distinction worth drawing. Laplace's demon is a thought experiment in principle if you really had perfect information. All the discussion about how chaos theory says you can't make predictions is only in practice, in the real world. But even before we knew about chaos theory, no one in their right mind thought you could make perfect predictions about the future in practice, because none of us is close to being Laplace's demon. So there's no sense in which chaos, etc., overturned the idea of Laplace's demon. Bill Warner says, I understand classical uncertainty. There are some pairs of quantities such as position and velocity or frequency and phase that are defined in such a way that the more you know about one, the less you know about the other. But Heisenberg introduced Planck's constant, h, to this otherwise unremarkable relationship, and it's totally thrown me off. How am I to interpret Planck's constant in the context of uncertainty? So you've thrown together a bunch of things that don't quite fit. You say some pairs of quantities such as position and velocity or frequency and phase are defined in a way that the more you know about one, the less you know about the other. But that's not true. Position and velocity are an entirely different case than frequency and phase in classical mechanics. In classical mechanics, there's no uncertainty relationship for position and velocity. In classical mechanics, you can know exactly, if you're Laplace's demon, for example, you could know precisely the position and the velocity of a particle. There's absolutely no reason why not. Frequency and phase are defined for waves, not for particles. And to discuss the frequency of a wave or the phase of a wave, you need more than information at a point. Right? You need to understand what the wave is doing over some finite interval. And so when you have a wave like that, then there is uncertainty between quantities like frequency and phase. But particles don't have that uncertainty at all in classical mechanics. The reason why they have it in quantum mechanics is because particles are now waves, right? They are wave functions. And the things that we call position and velocity are not properties of those waves. They are potentially observable quantities. And quantum mechanics, famously, the whole reason why quantum mechanics is hard is because what is observable is not what exists when you're not observing it. So this wave-like thing exists, the wave function, when you're not observing it. But then when you measure it, when you observe it, you see either position or velocity. And there are ways of extracting information about that wave function that are incompatible with each other. If you get definite information about position, you have completely destroyed information about velocity in quantum mechanics, or vice versa. So it is purely a quantum mechanical phenomenon that this uncertainty principle applies to things like electrons or quarks or so forth. Douglas Albrecht says, the wave function for a single particle allows for a small probability of a superposition of very different positions. These distances could be further than the speed of light would allow. Why is this any less strange or different from the spooky action at a distance when we try to understand entanglement? So I think you got to clear some things up once again here. The wave function for a single particle allows for a probability of a superposition of very different positions. Yes, that is true. You say these distances could be further than the speed of light would allow. By itself, that sentence doesn't quite make sense. What you might mean is if you were to measure the position of a particle, then you find that it is somewhere, and you know instantly that it is not somewhere else, and that somewhere else could be the speed further than the speed of light away, right? It almost inevitably would be, in fact. So you need to include the measurement process there. Just having a wave function spread out doesn't have anything to do with the speed of light. So the point you're trying to make is, when I observe the position of a single particle, the wave function changes simultaneously all over the universe. And that sounds like it is incompatible with special relativity just as much as Alice and Bob and entangled particles does. So the reason why we always talk about the entangled particles is you're imagining a world where the current theory of quantum mechanics isn't necessarily the final theory, right? This whole discussion is in the context of, could we improve quantum mechanics to a position where these puzzles don't occur? And so if all you had were one particle, you could always imagine the wave function was somehow just a way of talking about your uncertainty about it, right? Your lack of complete information. And you could imagine that when you observe its position, you're learning something about the universe you didn't know before, but you're not changing the universe in any particular way. The particle was always located there, you just didn't know it, okay? You can get away with that if you just have one particle. But if you have two particles and they're entangled, you can no longer get away with that. That's the point of the Bell inequalities. John Bell showed that there's no way to secretly have real once and for all true information about the spins or momenta of entangled particles in a way that is purely classical and yet purely local at the same time and be compatible with what we now know are the experimental outcomes. So you really need that entanglement there to get something that you would call a puzzle in the first place. Abdul Rahman Al-Jurbuwa says, I am wondering about your opinion on procreation from a moral standpoint. I don't have much of an opinion about procreation. I'm not even sure what you're getting at, whether it's like good to procreate or bad to procreate. I think that procreation is more or less morally neutral. I don't think that that is a intrinsic good or an intrinsic bad. You know, if you've been listening for a long time, you know that I am a moral constructivist. I'm not a moral objectivist or a moral realist. So I don't think that there are once and for all rules built into the structure of the world that tell us what is right and what is wrong. We invent the rules, okay, ultimately. And there's still rules. They're still there, and they still mean a lot to us, and it matters what rules we invent, but they're subjective. They're things that we construct as human beings. So it seems clear to me that some people are going to be very much in favor of procreating, and some people are not, and that's fine. As long as they don't interfere with each other's choices, that's completely fine. Even though that answer I just gave you was kind of uninteresting and unilluminating, the reason why I included this question was because I think that there is an interesting difference. Well, this kind of question, I guess I should say, is one of the things that leads me to be skeptical of utilitarianism, right? Utilitarian approaches to morality try to invent a quantity that they call the utility, the net utility of everything that happens, okay? And they say that the idea is to maximize the utility. And there are various thought experiments that show that if you really wanted to maximize the utility, you would make as many people as you could. You would procreate like crazy. Even if those people were miserable, you could always make enough of them that there would be more utility than otherwise. And that's just very counter to my own moral intuitions entirely. So I do think that thinking about giving birth to new generations is an important thought experiment for moral philosophy, but I don't have any strong opinions about whether it is intrinsically good or bad. Vladimir Yoff says, is the Higgs field potential the same across space-time? If it's not, does that mean the masses of particles like electrons will be different in different parts of the universe or changing over time? So today, in the universe today, so that is to say, at a slice of space-time, which we can call space at this moment of time, in some reference frame that you pick, the Higgs field is constant everywhere. So there's a good reason to think that. It's built into the fundamental equations. It's not varying or anything like that. So we do expect the masses of electrons or quarks to be the same everywhere in the universe. However, even though the potential, which is the sort of equation or the function that sets the minimum value of the Higgs field, is constant, the actual value that the Higgs field takes is not constant over time. That's because in the early universe, when there's a lot of heat and thermal radiation and things like that, the effective potential, as we call it, changes because the Higgs field is buffeted around by all of the hot plasma interacting with it all the time. And rather than falling down to some non-zero value and giving mass to particles, at very high temperatures, the Higgs field sits at zero value, at the center of its potential, rather than at the brim of the Mexican hat, where it usually lives today. So the Higgs field is not constant over time, and indeed, the mass of the electron or the mass of the quarks was zero at early times. Now, even saying that, you have to be careful because the mass is zero in the vacuum, but you're not in the vacuum, right? You're in this plasma. And so there will be plasma effects that can, in some sense, give particles who are charged particles an effective mass, but that's a more complicated thing. To answer your question, the Higgs field value is not the same in space-time, but it is the same throughout space today. Josh says, what are your thoughts on the ship of Theseus? So I think that you mean the ship of Theseus, unless there's a different ship that I don't know about. The ship of Theseus is something that I talk about in the big picture, actually, so you can read about it there. It's a thought experiment where Theseus has a ship, very famous, ancient Greek hero. They preserve the ship, put it in dry dock as a little memorial or whatever. But then over time, different parts of the ship kind of rot away and they have to be replaced. And eventually, like every individual piece of wood on the ship has been replaced by another piece of wood, but it's still in the shape that the original ship had. And so the question is that still the ship of Theseus? Like if you replaced one piece of wood, then it would still be the ship of Theseus, right? But if you replace all the pieces of wood, then maybe you're thinking it's not anymore. So what's the cutoff? And I think, I think this is an important thought experiment. And the reason why I think it is because to me, the answer is perfectly obvious, which is that the notion of continuity of identity over time is a macroscopic, approximate, emergent notion. It's not fundamental. The reason why I talk about it in the big picture is because I'm talking about living beings, right? People change over time too. The actual atoms in their body get replaced. Many of them do over time. And they maintain more or less the same shape, but not exactly. Like, you look older 20 years later than you look today, etc. You have more memories, all of those things. But there's some notion of continuity. And that notion of continuity has to do with the pattern being described over time rather than the specific atoms of which you are made. And I think that's the lesson of the thought experiment of the ship of Theseus. If you want to push it, so like the extra bonus level of the thought experiment is, well, what if they had repaired all those pieces of wood in the ship, but someone had saved all the original ones and then put together all the original ones? Would that be the ship of Theseus? And you can say the same thing about people in thought experiments like Derek Parfit had his famous teletransporter thought experiment where you get into a Star Trek-like transporter machine, but by mistake it creates two copies of you rather than just one, which is the original. Clearly, this has some relationship to the many worlds interpretation of quantum mechanics, right? There's one of me right now. If I generate a quantum random number and branch, then there'll be two of me. Which one is the real one? Well, the answer is neither one. There's no such thing as the real one. They're both continuous in some sense with that original pattern, and we should give up on treating identity over time as some fundamental feature of the universe, because it's just not. Jim Murphy says, as an eternalist, I know you view all of time as equally real. I wonder if the same could be said about all of Hilbert space. Is it likely that all possible states of the universe are equally real, or is it more likely that many of these states will never be reached? It's a slightly tricky question because on the one hand, this goes back actually to the Platonism question. On the one hand, I want to say what's real is the universe, okay? And but the universe at different times, not just the universe at one time. So from the Hilbert space point of view, what that's saying is what's real is a path through Hilbert space that is followed by the quantum state of the universe as it evolves. So you can think about that. You can be mathy about it, and you can say, well, does the wave function of the universe evolve through almost all of Hilbert space, or does it stay confined to a small region? And the answer is actually, wait for it, it stays confined to a small region. The wave function of the universe never evolves all through Hilbert space if the universe is a closed system, which I take it to be. So in some sense, quantum mechanics only uses a tiny part of Hilbert space. So maybe only that part is real and the rest is not, but that's weird because the whole Hilbert space is a much simpler mathematical structure than just the tiny part that is actually used. So I don't know is the short answer. And this is very much in line with me not having strong opinions about mathematical Platonism. When you say, is this or that mathematical structure or physical hypothetical structure real or not? I don't know. I'm more comfortable saying that other moments of time are real because they're physically really there. But parts of Hilbert space that the universe never reaches, I'm less sure about one way or the other. I mean, probably if you forced me, if you gun against the head, I would say we use the idealization of Hilbert space, but it's not real. There you go. The parts of that we don't reach should not be considered real. But I'm not 100% devoted to that opinion. Nicholas Weiberg says, if closed time-like curves existed, what would the experience be like to travel around one? Specifically, what would happen with the thermodynamic arrow of time? So closed time-like curves are, subsets of space-time in universes where you can start from one point on the closed time-like curve, locally travel forward in time along that curve, and yet you come back to exactly the same event in space-time, the same point in space and moment of time, not just the same point in space at a different moment of time. That would be a closed time-like curve. They probably don't exist in the real world, so that's the simple cheating answer. They don't exist. But you can ask, could they possibly exist and what that would be like? So it's almost inconceivable that anything macroscopic could literally travel around a closed time-like curve. You could travel around pretty close, right? You could imagine a person starting on a closed time-like curve, going around the loop and coming back almost to where they started, but they can't come back exactly to where they started because their earlier self is there. They're in the way, right? They haven't left because it's the same point in space-time. And you can't really imagine just joining back up. That's not a physically realizable circumstance. So maybe you can imagine a certain individual photon that is perfectly on a closed time-like curve, but even that I wouldn't really take seriously. So most of the time when physicists are talking about traveling around a closed time-like curve, they mean traveling within some set of space-time that consists of closed time-like curves, but not literally on the same curve. And about the thermodynamic arrow of time, nothing weird happens. You would have to have entropy increasing. How that's supposed to work out? Okay, that's a good question, right? Like entropy increasing is a feature of the whole universe, whereas closed time-like curves map different parts of time onto each other in interesting ways. So the way I like to say it is, the reason why we have trouble with time travel at all is because you think, according to the laws of physics, that the past is fixed and the future you can make choices about, right? That's the arrow of time gives you that impression. Of course, if you were Laplace's demon, that wouldn't be true, but you're not. Okay, so you think you can make choices about the future, but the existence of a time machine or a closed time-like curve mixes up your individual notion of the future with the universe's notion of the past. And then it's hard to make sense of these particular things. So you would have to tell me exactly what kind of scenario you meant or you had in mind with the closed time-like curves. But my impression was any working scenario would have the arrow of time going on as always. Maybe there are no working scenarios like that. That I'm not sure about. David Grimes says, PBS Spacetime recently published a video explaining that the lack of a theory of quantum gravity leaves us with no real sense of what happens to a black hole just before Hawking evaporation would dismantle it. There might not be an allowed transition to permit the black hole to emit a necessary final photon with sufficient energy for it to pop, and thus such Planck relics that might have been formed in the extreme energy densities before and during inflation might account for dark matter. Since such relics would have the Planck mass and event horizons spanning the Planck length, is there any reasonable prospect that we'd be able to observe them or rule out their existence? So the idea here, in case that wasn't sufficiently clear, my reading of it, most of the time when we think about black holes evaporating, we imagine they evaporate all the way. They completely disappear. But we're not sure about that. It's possible that they evaporate just down to the Planck energy and they stop. So you're left with a little relic or a little remnant. Now, there are very good reasons to not believe that, okay? If those relics existed, they would have a lot of entropy. Sorry, not a lot of entropy, but there would be a lot of different ways of making them. Let's put it that way. And therefore, they could have bad effects in virtual processes, Feynman diagrams, things like that. There would be a lot of different kinds of black holes that could do a lot of different kinds of things to particle physics. So it's a very, very, it's not a very popular theory, let's put it that way. But maybe they're there, and maybe they could be the dark matter. However, there's another puzzle, which is where did all these black holes come from? So in this scenario, where black holes are the dark matter, you have to imagine you've made a huge number of black holes, and then they almost completely evaporated away. Most versions, there are stories of how black holes could be produced in the early universe and be the dark matter. But in those stories, usually the black holes are taken to be pretty massive, right? You know, the size of the Earth or something like that, or Jupiter or whatever. And so there's a lot of mass in each black hole, so you don't need to make as many of them. If your black holes are only the Planck mass, you need to make a huge number of them. And how do you do that? That's just very hard to imagine. Finally, to actually answer your question, as far as I know, no. It would be very, very, very hard to detect them if the dark matter is Planck mass particles with Planck scale interactions. Planck scale interactions are very weak interactions. They're gravitational strength interactions. And if you think about it, you know, the Planck mass is 10 to the 18 times the mass of a proton. So even if the density of dark matter is 5 or 8 or whatever times the total density of ordinary matter, the number density, the number of particles per cubic centimeter, if they were Planck mass relics, is very low, very tiny compared to the number density of ordinary matter. So number one, the chance that you would actually run into one is much smaller than for other theories of dark matter, where the particles are much less massive and they're more numerous in the universe. And number two, they interact very weakly. So they would be much harder to detect than an ordinary, conventional, weakly interacting massive particle. Doesn't say you absolutely can't, but it would be very, very hard to do. I know of no way that would be guaranteed to be able to do it. Let's put it that way. Justin Bailey says, I know that measuring the spin of an electron is subject to superposition, that is, uncertainty. Are there cases where that is true of the type of particle itself? Are there cases where a particle could be an electron or a muon, an electron or a photon? So, you know, kind of. I wanted to say originally no to the answer to this question. In practice, no. In practice, there are no cases where a particle could be an electron or a muon. You could try to create one. You could try to create a wave function for the quantum fields of the universe that was sort of half electron and half muon. But the point is that because the mass of the electron and the mass of the muon are so different, the part of the wave function that was electron would just quickly separate itself from the part of the wave function that was a muon, okay? So they would quickly distinguish whether it was one or the other. There is one, and if it's an electron or a photon, it's even worse because the photon's always moving at the speed of light, and the electron is electrically charged. So those two particles are so different that there's never a case where it would be even tempting to think about a superposition of two types of them. The one exception to that set of rules is neutrinos, because neutrinos are all very light. There are three kinds of neutrinos: electron neutrinos, muon neutrinos, tau neutrinos. They have different masses, but they're all low mass, so they're typically all moving close to the speed of light, and they all have the same quantum numbers, right? They're all zero charge, spin 1/2. So you might imagine that you could create a superposition of different kinds of neutrinos. And guess what? You do. This is the whole subject of neutrino oscillations. When you create a neutrino, you create an electron neutrino or a muon neutrino or a tau neutrino, right? That's what happens in the particle physics process that makes a neutrino. But there are also three different masses of neutrinos. There's the lightest one, the middleweight one, and the heavyweight one. And I have to distinguish those because each mass state is a superposition of the different flavors, as we say, neutrinos. So the lightest neutrino is part electron neutrino, part muon, and part tau neutrino. Likewise for the middleweight neutrino, and likewise for the heavyweight neutrino. So what this means is that the neutrinos can sort of oscillate back and forth between different kinds. If they're moving through matter, then those oscillations happen in a certain way that can be detected and help you explain the solar neutrino problem. So these have been observed in experiments. Neutrinos really do oscillate. And you can think of that very much like the quantum uncertainty in a spin or something like that. Hilbert Spaceman says, do you have any insight as to what motivates publish or perish from the perspective of the people who run universities? Why are they biased towards frequent rather than high-quality publishing? Yeah, I mean, that's a good question. It's a tough question because different people are different, right? I mean, you say the people who run universities, but there are presidents, there are provosts, there are deans, there are chairs, there are faculty members who are in their department and don't have a title but are nevertheless very influential. You know, it's a whole bunch of voices come into this game and they don't all think in the same way. Certainly, we would like to think that what matters is the quality of the research you do, right? But guess what? How do you measure what the quality is? One way is to read the papers, right? To read what people actually have written. As a practical matter, if you're the provost, so you're overlooking the tenure cases of every single faculty member in your university, you're not going to read all their papers. You wouldn't even understand them. Most of them are in fields you know nothing about. You have no way of judging whether they're high quality or not. The faculty should be able to do a better job, but as you maybe know, in physics or biology or whatever, mathematics, these are such highly specialized fields that it is very often difficult for even a person in the same department to read and pass judgment on the papers written by somebody else. So we turn to proxies, both because of the practical and the in-principle difficulties of this. So you turn to how many citations did the paper get? I think that that's one of the more reasonable proxies, actually, for quality. High-quality papers have a big impact. Lower-quality papers don't. But it's clearly not a very good one. I mean, even so, just to be clear, even if it's one of the better ones, that doesn't mean it's very good. Because obviously, you can write a paper that is very, very important and goes years without getting any citations. I know that because Steven Weinberg's paper establishing the electroweak theory got no citations in the first several years after it was published. And then it took off once we had reason to believe the electroweak theory was probably right, and it became the most highly cited paper in all of physics. So you could have made a mistake if 5 years after the paper was published, you judged it on the number of its citations. But even that's better than what a lot of departments do, which is just to look at the journal you published it in, right? If you publish it in a high prestige journal, that counts better than if you publish it in a low prestige journal. And the lowest possible filter, sort of the dumbest possible filter is, like you say, just how many papers are there that this person published. I'll be very honest, I'm on various committees to look at prizes and things like that. And if someone publishes too many papers, in my mind, it can count against them. By too many papers, I mean, like, there are people out there who publish over 50 or 100 papers a year. That's more than one a week. How do you do that? Well, clearly you're barely reading those papers, much less writing them and doing the research. You're part of some bigger group that is doing a lot. You're putting your name on it. Maybe you're having many papers that are very tiny variations on each other, and so forth. So there's a point of diminishing returns. But all of this is to say that whenever you have a situation where many people are being evaluated, sadly, in the real world, the evaluations are not always going to be as careful as you would like them to be, especially when they're being evaluated at a very high level by the provost, the dean, the president of the university, or whatever. I'm not trying to excuse it. I don't think it's a good system. I wish that there was much more room in academia for sitting and thinking for 5 years and then publishing something really brilliant, rather than publishing several things every year, none of which are brilliant. The obvious problem with that ambition is, if you say, okay, sit and think for 5 years, you don't need to publish anything, 99% of the people in that system are not going to publish something brilliant at the end. They're just going to publish nothing. So at least if you're publishing lots of things, then you're doing something, right? It's a very crude, very inadequate, very unsatisfying system. But it is hard to have reasonable, realistic systems that would be completely different than that. Sherman Flips says, you mentioned coming from a working class background. When you got into science and philosophy, how did you find people to talk with about those things? Was it all people in the same education system, or did you find people elsewhere? Well, if we're talking about like when I was in high school, we didn't have the internet back then. I have to, show my age here a little bit. And basically, I didn't talk to people about science and philosophy. I was interested in science. I didn't know anything about philosophy when I was in high school. I had smart people in my high school, big public high school, smart friends and so forth. But science wasn't one of the things we talked about. I was on the debate team and we talked a lot about policy questions because I was on the policy debate team. So we talked about politics and economics and things like that, less so about science. And when I got to university, I was surrounded by suddenly people who did care about science and philosophy, and I talked to them. So I didn't have any secrets to reveal to you. Sorry about that. Mikolaj Szabo says, I'm having a hard time wrapping my head around this fundamental principle that the laws of nature must be reversible, information must be conserved. In our everyday life, we are surrounded mostly by irreversible phenomena, even when it comes to abstract things. So clearly not everything must be reversible. Why is it then that the state transitions of the universe are such that a successive state is mapped onto exactly one prior state? So I think I'm getting a different vibe from different parts of your question. There's no fundamental principle that the laws of nature must be reversible. That's just not a principle. That is a fact we figure out about the laws after we invent what the laws were. So it's not that we start from a presupposition that the laws of nature must be reversible. It's that we invent the best laws we can, whether you're Isaac Newton or Albert Einstein or whatever, and lo and behold, they're reversible. Okay, that they just are. And so we call that a principle that we invented after the fact. In fact, it was literally Laplace who invented conservation of information a century after Isaac Newton had invented these rules that have this principle embedded into them. So that principle could be wrong. We don't know what the fundamental laws are. Maybe they are irreversible. But our best idea today of what the fundamental laws are have the feature that they're reversible. That's just a fact. One of those brute facts about the universe that I think we have to accept, as I said. Herb Berkowitz says, what did you think then and what do you think now of the demotion of Pluto in the solar system? Good. So I'm glad you asked this question because it's an example of me changing my mind. When that first came up, the whole demotion of Pluto thing, I was on the side of the people who said, this is just silly. We've already labeled Pluto to be a planet. Why are we working so hard to unlabel it? Just, grandfather it in, call it a planet, and then invent another definition of planet that will apply when we go to other solar systems, other stars, things like that. But, my mind was changed by talking to people who knew more than I did. In fact, Mike Brown, who was a guest on the Mindscape podcast back in the day, old school guest for those of you newcomers, listen to the interview with Mike Brown. Mike is the single person who is more responsible than anybody for getting Pluto demoted. Okay, Pluto Killer is his Twitter handle. Because he discovered all of these other objects in the Kuiper Belt out there in the outer solar system, which are just as big as Pluto, very Pluto-like. And there's zero reason to think that you should have Pluto be in one category and all these other objects be in another category. So as Mike says, look, all of his incentive was to keep Pluto as a planet. And in that case, he would be credited for discovering more planets than any other person ever in the history of astronomy. But he says, intuitively that doesn't make sense. These are just little rocks out there at the edges of the solar system. They don't deserve to be planets, and neither does Pluto. And there is something important. There's a relationship, and I think this is the argument that changed my mind from Mike and from others. There is a relationship between how we talk and how we think, right? Language is arbitrary. We can invent whatever words we like. We can invent whatever definitions we want to for the words. But if the words we invent and the definitions we have for them don't map onto some feature of reality, then they don't help us think. Having a definition of the word planet that can be extended beyond our solar system consistently, so we can say what we call a planet and what we don't, helps us think about planets in a careful, precise way. And we're entering an era now where we're discovering more and more planets around other stars. So now is the time to get our house in order, to figure out what we mean by planet. And there's really no good definition of planet if you just came up with one carefully by which Pluto would count. So now I'm on the side where Pluto should not count as a planet anymore. Crather Luca says, can you explain why Bayesian reasoning is not just inductivism with extra steps? And if it is, then why do you believe it is important to try to be a good Bayesian? I think it's quite different, actually. I mean, Bayesian reasoning can be thought of as what inductivism should have been all along. I hope I'm interpreting the word inductivism correctly. I know what induction is. I presume that inductivism means using induction to learn more about the world. So there's mathematical induction or logical induction, which says if I know something is true for, if I have a whole set of things, thing one, thing two, thing three, thing four, etc. If I know if a certain property is true for thing zero, the first thing, and I know that if something is true for thing n, then it is true for thing n plus 1, I can inductively demonstrate that that thing is true for all the things, right? I go from the zero thing to first to second to third, etc. That's mathematical logical induction. Zero problems with that. That's just logically completely valid. There's also sort of a more empirical kind of induction, which is you say, oh, I see a swan and it is white. I see another swan and it's white. Oh, look, I see a dozen swans. They're all white. I therefore extrapolate out into the world and say swans are always white. Okay, that's a sort of more empirical kind of induction. But that's also nonsense. As David Hume famously pointed out, all we have to do is tomorrow see a black swan and we would change our mind. He wasn't using the swans, I don't think, but other people have used that example. You can never be sure that tomorrow you won't see a violation of your rule. You don't have certainty in that step that you have in mathematical induction that if something is true for thing n, it must be true for thing n plus 1. That's what you're trying to prove, so you can't assume it and then draw a deduction from it. What you should do instead is be a good Bayesian, which means rather than saying, oh, I've seen 12 white swans, therefore all swans are white, you should say, well, I have a theory that all swans are white. I have another theory that some swans are white and some are black. And I give a certain credence, a priori, prior credences to these two theories. And then I observe some swans. And, you know, if I have a theory that says that half of the swans in the world are white and half are black, and they're equally distributed uniformly through the world, if I observe 12 swans in a row and they're all white, that is very strong evidence against the 50-50 theory. If the swans cluster so that all swans in the northern hemisphere are white and all swans in the southern hemisphere are black, then the fact that I observe 12 white swans in the northern hemisphere is completely unsurprising, gives me no evidence whatsoever. So that's the right way to do it, right? So it's not just inductivism, it's the other way around. Inductivism is a sloppy preliminary version of Bayesianism, is what I would say. Hannes Stark says, you said something along the lines of, in your podcast, you want to let the other person speak and give them a platform to share their ideas and opinions instead of you talking and giving your opinion. However, for me as a listener, it is likely that I come to your podcast because I think you have valid and interesting opinions and often would like to hear more about how you judge some ideas and your opinions on them. What do you think of bringing more of your views into the podcast? This is always a balance, right? This is a perfectly legitimate question, but my attitude is, I do want to let my opinion be known, and I try to do that in the podcast, in the conversations I have. When I disagree with somebody, usually I will say that I disagree with them, and I will even try to very quickly give my reason why. What I don't want to do is debate back and forth. What I'm trying to do is educate the people who are listening. So I want them to know what my opinion is and the reasoning behind it. But really, I want you to know I'm bringing some expert, someone who knows a lot about some subject, and I want you to think about what they're saying, whether or not you or I agree with them. I want to enter into the mind space of thinking about what it would be like to agree with them, right? To try to really understand where they're coming from their point of view. Even with all that, the amount of time I spend talking in any one podcast is smaller than the guest is spent talking usually. But if I integrate over many, many episodes of the podcast, I do a lot more talking than any individual guest does. So I think, and especially because I have AMAs and solo podcasts and things like that, most people are going to hear my opinions way more than any one guest on the podcast. I don't think there's any shortage of my opinions being put out there into the world. And if you have, if you ever want to know more about my opinions about some specific thing, here you are. Here's the AMAs. This is a great time to ask about them. Some of my favorite questions to answer in the AMAs are follow-ups to the podcasts. I have people on the podcast for reasons. I think that what they say is interesting. And so, talking about that stuff is a lot of fun to me. Hugh H. says, if a speeding cannonball travels further than a Wimbledon cross-court winner within the set time period given, and both balls are released at the same moment, does the speeding cannonball also entangle with more particles than the tennis ball on its journey? Good. So this is a good question. It took me a while to sort of interpret this question. What you mean is, if a big thing and a tiny thing are both moving at the same velocity, does the big thing entangle with more particles than the tiny thing? No. Roughly speaking, no. There's probably some fuzziness around the edges here because quantum mechanics is hard and there's a lot of approximations we're making. But the point is, when a big macroscopic object is flying through the air, roughly speaking, it's not entangling with anything at all. It's interacting with things, right? But it's different. The difference is Schrodinger's cat, okay? In the case of Schrodinger's cat, you have a cat that is in a superposition of awake and asleep. And that means that the two parts of the superposition of the cat are physically located in different places. And therefore, a photon that has, a location in space will hit the cat if it's in one part of the superposition, but miss it if it's in the other one. And that's what branches the wave function of the universe. And then it has two different branches, one where the cat's awake, one where the cat's asleep. But once that happens, once you're in one branch where the cat is either awake or asleep, another photon either hits the cat or it doesn't, right? In one branch, forget about the other branch. In any one branch, when you have a situation where the object has some macroscopic coherence, a photon will either hit it or not. Neither one of those interactions, hitting or not hitting, is an entanglement, right? Entanglement means different parts of the state of one system become differently interacting with different parts of the state of the other system. So in the case of Schrodinger's cat, you have the environment with all sorts of photons, and you have the cat, which is awake and asleep, and they become correlated, connected with each other. In the case of a tennis ball or a cannonball or an awake cat, the photons either bounce off them or they don't. There's no correlations that are induced by that. Again, this is not precisely true because the photon could be in a superposition of being in one place or another place, and maybe the big object has more of a probability to entangle with that kind of photon. But roughly speaking, once you're classical, once you're big and coherent and in some branch of the wave function, you're not constantly entangling with things around you. That's kind of a more special event. Stephen Lyon says, in the biggest ideas, you briefly touch on the evolution of particles as they squeeze past neutron degeneracy pressure, as in a collapsing black hole, and that the collapse becomes runaway. You briefly mention quark stars, but past that point, information everywhere seems to dry up. Do we have any conception of what happens when quark degeneracy pressure is surpassed? So the answer is yes and no. Do we have any conception? The reason why we don't hear much about it is that there is no reason we have to think that there is another step beyond quark degeneracy pressure. Okay, so what we're talking about here is when you have a white dwarf star. So a white dwarf is a star which has given off, it's radiated all of it's done all the nuclear fusion it's going to do. It's cooled off and shrunk and is held up by degeneracy pressure. The electrons in the neutron star are packed as tightly as they can be packed. But if it accretes more matter, Chandrasekhar showed a long time ago that there is an allowed transition where the electrons combine with protons to create neutrons. And the whole thing just becomes a neutron star. Okay, so a neutron has a much smaller wavelength than an electron does. So if you convert all those electrons into neutrons plus the protons, the electrons plus protons get converted into neutrons, the whole thing is much smaller and you get a neutron star. So you might ask, as is being asked now, well, if you just squeeze the neutron star, what happens? It has a pressure, degeneracy pressure from those neutrons. What if you have a gravitational force that is greater than the degeneracy pressure? And the short answer is, what we think happens is, it just collapses to a black hole. There's not like one or more or an infinite number of intermediate steps. It just collapses all the way to zero. It's easy to say that, but it's hard to prove because you're at this interface of quantum field theory and general relativity, right? Which is a place where we don't know a lot about. Plus, you're into questions about quantum field theory and particle physics itself that we just don't know a lot about. Are there smaller things than neutrons that it could collapse into? And that's where you get strange stars and things like that. But the reason why the information seems to dry up is because, as far as we know, there are no steps in between neutron star and black hole. P. Walder says, are Bayesian and Popperian approaches to getting closer to truth both valid, or are they mutually exclusive? I should have combined this one with the inductivism question, because I would say the same thing, namely that the Popperian approach to truth is a crude approximation to the Bayesian approach to truth. And not everyone will agree with that, but I think it's right. What Popper says is, imagine all the theories, okay? Imagine all possible hypotheses. He had a book entitled Conjectures and Refutations. So imagine all the possible conjectures you should make about the world. And what you should do, according to Popper, is treat all of them as potentially true and collect data that says, oh, nope, that one is false. So you slice away the false ones bit by bit, and you're left with the truth. That is the Popperian way of reaching the truth. So this is not what people actually do for all sorts of reasons, mostly because, just like with the induction discussion we had before, it assumes a level of certainty or of definitiveness that is never there in the real world. When you have a conjecture, let's say your conjecture is Newtonian gravity is correct. That's your conjecture. You do an experiment and you find that you are not agreeing with the prediction of Newtonian gravity. Do you throw away Newtonian gravity? Well, we did that for the motion of Uranus. When the planet Uranus was discovered and we tracked its motion through the sky, it was not agreeing with the prediction of Newtonian gravity. Did we falsify Newtonian gravity? No. We said maybe there's another planet out beyond Uranus. We call it Neptune, and we eventually found it. The same thing happened with Mercury, right? The planet Mercury's motion around the sun was not compatible with Newtonian gravity. Did we falsify Newtonian gravity? Actually, yes, this time we did, because general relativity was the right theory. So the Popperian falsificationist approach as a program for doing science isn't very popular these days, just because the refutations part of conjectures and refutations are never quite as cut and dried as he would like to have you believe. How do you fix it? How do you improve on that situation? How do you take into account the fact that they're not very cut and dried? The answer is called Bayesian reasoning, right? You say, well, what is the probability that I would get this kind of experimental outcome if this theory were true, etc. So I think that, Popper is the limit of Bayes, where you set certain experiments, certain likelihood functions to being 0 or 1. But I think as a good Bayesian, you should never do that, because maybe you made a mistake in your experiment. You always have to consider the possibility, as small as it might be, that you might have made a mistake. And Bayes lets you do that. Carlos Nunez has a priority question, which is, many scientists have recently put forth the lab leak theory for the origin of COVID-19 as a viable option. Have you updated your Bayesian priors based on this new information, and what probability do you grant to this hypothesis vis-a-vis the zoonotic origin alternative? Yeah, I've updated a little bit, but honestly, I don't have strong credences one way or the other. I never really followed the discussion about the origin of COVID-19. So it's completely plausible to me that it started in, a wet market or whatever. Completely plausible to me that it started in a lab and leaked out. And so I believe what they tell me, roughly speaking. I haven't really followed what the experts are saying. Again, that's not a very interesting answer to your question. Why am I answering it? I think that this is an interesting sociological case in how we talk about these situations. I think that it's important to distinguish the hypothesis where there was a lab that was doing work on coronaviruses, and they developed one either intentionally or unintentionally in the course of their experiments, and it leaked out. Okay, that's a hypothesis. There's another hypothesis is that the coronavirus, the novel coronavirus that gives us COVID-19, was intentionally developed as a bioweapon and set free. Okay, these are two separate hypotheses, but they're kind of next to each other. And I think that early on, this bioterror explanation was given more credence in certain circles than it should have, just for political / cultural / racist reasons. And it was a mistake to give too much credence to that because you wanted to blame somebody, okay? But now the opposite mistake is being made. In certain circles, they're discounting the lab creation hypothesis because they don't want to give credence to the racist hypotheses, okay? I mean, maybe it was a bioweapon. I don't even know that. As far as I know, that's plausible. But I know that that idea was leveraged for political reasons, okay? And there are people now who don't want to give credence to those political reasons, and therefore they also discount evidence that is in favor of the lab origin hypothesis. So I have no dogs in the fight about how the actual virus was created or where it came from. But I do think that we should put aside the political motivations for favoring or disfavoring one hypothesis or the other. We should take them all seriously if you care about that. I mean, if that's one of the things you're following. Like I said, I'm not really following it, but when you do, you should do so for scientific reasons, not for political ones. Scott says, you've taught us that the interaction with the Higgs field is responsible for the masses of elementary particles. More massive particles like a muon can decay into less massive particles like an electron with the additional mass converted into kinetic energy, photons, etc. Is there anything deeper about the Higgs field interaction that determines how these decays work or how mass is converted into other forms of energy? So the short answer is no. There are tiny little details, but they're very, very irrelevant at this level of analysis. The reason why, what I wanted to emphasize in the answer to this question is mass is mass once you have it, okay? The Higgs field is the mechanism responsible for giving mass to things like electrons and quarks, W bosons and Z bosons. But once that happens, the mass of the electron is just the mass of the electron. It behaves like the mass of the electron, and you can forget about the Higgs field. At low energies, indeed, you can completely forget about the Higgs field. All you need to know is what electrons do, what their mass is, how they interact with other particles, okay? Paul Dirac, Richard Feynman, etc., were very, very able to make calculations in quantum electrodynamics with electrons and their mass, not ever having heard about the Higgs field back in those days. And I think that when people hear that the Higgs field gives mass to these particles, they somehow attribute some essence of massiness to the Higgs field. And sometimes they go so far as to say, well, mass is important for energy and for gravity, and therefore does the Higgs boson have some connection to gravity? No, it really doesn't. The Higgs field is the mechanism responsible for giving particles mass, and mass has a connection to gravity, but the Higgs field has no connection to gravity because of that connection. Does that make sense? Once you know what the masses are, that's all you need to know. There's nothing deeper about that interaction. Okay, let's group together 3 questions here. Kevin Wolk says, wondering if you've read Carlo Rovelli's latest book, Helgoland. More specifically, assuming you have or are familiar with Rovelli and his ideas, I'd like to know if and on which points you agree or disagree with him. Rovelli does not seem to be as big a proponent of the many worlds theory as you are, as far as I understand both of your positions. Anders Strand Vestbov says, in his latest book, Helgoland, Carlo Rovelli reflects on his interpretation of quantum theory as relations. The world should be understood as a web of interactions and relations rather than objects. An object does not really exist without interacting with another object. To me, this sounds like a more blurred way of explaining the same as entanglement and branching of the wave function in the many worlds interpretation. Is it related in any way, or is it fundamentally different? And then Francis Day says, I've been reading Carlo Rovelli's paper on relational quantum mechanics and wondered what your take on it is. I've heard him say he was an Everettian, up to but not including many worlds, so I'm guessing you are not entirely on board. So, obviously, all these 3 questions are about Carlo Rovelli and his relational quantum mechanics, which he recently talked about in a popular level book called Helgoland. I have not read Helgoland, but yes, I am familiar with Carlo Rovelli. He was the very second guest on the Mindscape podcast. In fact, I think he was the first person I actually interviewed, although his interview appeared second. episode number 2. And we're friends. We get along. We have very different ideas about quantum mechanics. I have not read Helgoland because, number one, I don't read a lot of popular physics books, right? I mean, I read physics papers, but if I'm reading popular level books, it's not going to be physics generally. I get enough of that in my day job. And number two, I don't really follow his particular interpretation of quantum mechanics. I don't know a lot about it. It's not many worlds, not in the sense that I would define it or Everett would have defined it. He does, try to... He does not introduce hidden variables or dynamical collapses. So in that case, there's a family resemblance to many worlds. He does think that you need to have some preferred way of looking at the world, some preferred observables or something like that. And then, as the questioners say, he emphasizes the relational aspects of all these things. But so my short answer is no, I'm not very familiar with these works or this interpretation. But the reason why I wanted to answer the questions is to say, I don't know a lot about any other interpretations of quantum mechanics. I know a little bit about the main ones, enough to, teach them when I teach a class. Like, here are the basics of Bohmian mechanics or cubism or something like that, but only the very basics. And I do not either follow the large number of alternatives to the main contenders, nor do I get very deeply invested in any of the others. And the reason why is because I think that I have the right interpretation. I think that the Everett interpretation is the correct one. Now, as a good Bayesian, that doesn't mean I'm certain that it's right. I could certainly change my mind if evidence, either in the form of experiment or in the form of really good arguments, came my way. But I haven't heard those arguments, and therefore I have to act like a working physicist. I have to say, what am I going to spend my time thinking about? I could spend time thinking about alternatives to Everettian quantum mechanics and see whether or not I think that they're plausible and should be pursued. Or I could take Everettian quantum mechanics as my starting point and ask, what can I do within that, right? What can I do to relate it to the real world, to use that framework to develop better theories of cosmology and space-time and field theory and what have you? And I choose the latter point of view. And indeed, everybody does that, right? Everybody takes some either theories or views of the world as more or less what they assume is correct until other information comes in, and they move on from there, right? Otherwise, you're stuck in some terrible Cartesian skepticism scenario where you can't believe anything. Like, you don't know anything at all, and you have to start from, set theory whenever you start to write a new paper. So I'm just explaining why, even though I write a lot about the foundations of quantum mechanics, when people ask me about other formulations of the foundations of quantum mechanics, I'm just not an expert. I really don't follow that stuff very carefully. Speaking of which, the next question is, what are your thoughts on idealism as proposed by Bernardo Kastrup, which offers a more parsimonious explanation for reality versus the many worlds theory? Again, I'm not very familiar. I know I've heard of it, read a little bit about it, but number one, I certainly don't think it is more parsimonious than many worlds. Remember, many worlds is not a theory that says there are many worlds. It's a theory that says the quantum wave function, which exists in one form or another, plays some role in every single interpretation of quantum mechanics. Many worlds says that's all that exists, the quantum wave function, and the Schrödinger equation, which talks about how the wave function evolves under some circumstances in every interpretation of quantum mechanics. Many worlds says it's the only thing that says how the wave function evolves. There are no other modes of evolution, unlike collapse models or what have you. So in my view, many worlds is absolutely the most parsimonious explanation, the fewest equations, the fewest ontological elements. Now, idealism as a strategy, I'm, again, not very familiar with Kastrup's specific point of view on it, but it seems like a terrible strategy to me, and certainly not very parsimonious. Idealism being the idea that rather than putting the physical world at the center of one's ontology or view of reality, and showing how things like minds and thoughts and agents and experiences all arise as part of the physical world, idealism in some sense takes the mental world as the primary thing. Mental aspects of the world are what lead to our views that there is something called the physical world out there. This seems like just a terribly bad strategy, to be like a laughably bad strategy. What could be more evident than the objective reality of the physical world to me? I admit that when quantum mechanics came along, there was this sort of moment of weakness early on in the development of quantum mechanics when the fact that quantum theory drew a distinction between what we directly observe and what really exists opened a door for people to say, well, maybe we're bringing reality into existence by the way that we think about it. But now we know better, right? Now we have even if it's not many worlds, we have multiple purely physical, absolutely mechanistic theories that give you the quantum mechanical answers, whether they're dynamical collapse theories or hidden variable theories or many worlds or what have you. So that temptation, that moment of weakness has passed for most of us. And the idea that we should sort of forget this amazing fact that when we different human beings all look at the physical world, we come up with the same rules of behavior for it, right? That individual different people do not have different notions of the laws of physics. To me, that's more than enough to squelch any temptation there might be to be an idealist about the fundamental nature of reality. Stephen Bernard says, my question is about the possibility of universal principles behind complex systems. There are many examples of systems that appear to be complex in some sense, both natural and artificial, the brain, the cell, evolution, etc. But these systems all appear to be sui generis, one damn thing after another with little or no common features at a systemic level. Do you think it's possible to discover universal principles of complexity? Yeah, I do think it is possible to do that, although the word universal might be stretching it a little bit. I think there are common aspects of complex systems that appear over and over again. Maybe not in absolutely every single one, but in enough of them that you can say, okay, in these systems, we see these features. And the opposite features almost never appear, right? You see features like interactions over various scales. I want to say scale-free behavior, but that's a little bit too strong, but roughly scale-free behavior, right? Power law behavior for different important elements. You see subsystems coming together to show emergent behavior in conglomerations of these subsystems. You see information processing, right? You see that there are nonlinear ways in which influences from the outside world get thought about, if you want to be a little bit poetic, and then responded to by the complex systems. So I think that there's plenty of ways in which what we think of as complex systems do show commonalities. It's not that there is no it's not that there are no commonalities, it's that these systems are messy. They're big macroscopic things. It's like saying, I've met many, many people and they're no two of them are exactly alike. Therefore, do you think that there are no commonalities between people, right? No, I think there's actually a lot of commonalities between people and there are a lot of differences. That's a trivial toy version of the same thing I would say about complex systems more generally. Joe Growinski says, I'm combining two questions here. One is from Joe Growinski. In regards to the arrow of time, if I'm not mistaken, I remember you talking about the possibility of another arrow of time opposing our own that could have been created at the Big Bang. If that's possible, could it be possible for there to be other arrows that point in other directions? And Andrew Vernon Smith says, Julian Barber, in his book Janus Point, at the end of chapter 5, refers to a paper by Jennifer Chen and Sean Carroll, that would be me, and to an unpublished idea of Sean Carroll relating to fundamental equations of a theory for the temporal evolution of the universe that obey the first and second laws of thermodynamics and also have bidirectional arrows of time in all regions and at all times. Would you compare or contrast your ideas with those of Boltzmann, Feynman, Penrose, Barber, or whatever the consensus or leading theories may currently be? So I think that neither one of these questions got exactly right my own theory that I proposed with Jennifer Chen back in 2004. The idea behind our paper was there were basically two ideas, and this is always a mistake. Whenever you have two ideas, you should just write two papers because one of your ideas is either going to get forgotten or misunderstood because the other idea is going to take up all the oxygen, okay? And so we made that mistake. So the two ideas we had was, number one, a general fact about how one could go about explaining the arrow of time. The arrow of time is explained in our universe because entropy was low near the Big Bang and has increased ever since. That, to me, this is work to be done to show why this is true, but To me, that's the underlying thing that gives rise to the arrow of time in our observed universe. And the cosmological question is, why were initial conditions near the Big Bang so special, so low entropy? And there have been a lot of very, very bad attempts at accounting for this, up to and including people like Stephen Hawking making terrible mistakes about trying to explain the naturalness of the early universe. And so Jennifer and I, Jenny Chen and I, who was a student at Chicago at the time, we took very seriously the idea that if you wanted to explain the arrow of time without cheating, so without putting in an asymmetry by hand, the point is that the laws of physics show no asymmetry between the past and future. The arrow of time does, but you don't want to explain that arrow of time by putting in an asymmetry. Otherwise, you're just explaining something by putting in the same thing, right? You're begging the question. So given that our early universe had low entropy and our late universe has high entropy, how in the world can you explain that without putting it in by hand? And the answer that we came up with is you need the conditions in the far, far past and the far, far future to be similar to each other, right? That's the way. That's the only way, basically, that you can imagine a dynamical origin for the arrow of time without cheating. So if we think that our future is going to be high entropy, the solution would be to say that the past was high entropy. But we know that the immediate past wasn't high entropy. By immediate, we mean the last 14 billion years. So you say that the Big Bang was not the beginning of the universe. There was something before the Big Bang. And the temptation, this is an old idea that the Big Bang was not the beginning of the universe. The temptation when you do that is to make the Big Bang the middle of the universe, right? To say that there is some special moment at the Big Bang where things are symmetric about that moment. So maybe there is a past in which there's a Big Bang going in the other direction, and there's a future, that we live in where the Big Bang goes in our direction. But that doesn't really explain the arrow of time. You're just making it a middle condition rather than a past condition, right? And so you haven't explained why that's true. So our idea is not that there is a past that is similar to our Big Bang universe popping out of the Big Bang in the other direction, but rather that our Big Bang universe arose out of empty space. We know from observations that empty space has a small cosmological constant, at least in our observable universe, so let's just take that for granted. And we pointed out, using ideas from Alan Guth and Eddie Farhi and others, that it's possible, not something we know for sure, but it's possible that empty space is unstable to bubbling off a little baby universe. So you can start with empty space, no arrow of time, nothing going on, but time is still passing, and it's metastable in some sense. It's almost the highest entropy possible state, but entropy can always increase by creating new universes. So the two ideas, to go back to the two ideas that we had, one is you can explain why entropy is increasing naturally by saying that entropy can always increase. By saying that there is a number you can assign to the universe called the entropy, maybe some finite number or some regularizable infinite number, but it can always go up. So if that's true, then given any value of the entropy, if you evolve it at one moment of time, if you evolve it both forward and backward and wait long enough, it will increase, okay? So that's one idea, that basically you can naturally explain why you see a gradient in entropy by saying that there is no equilibrium of maximum entropy for the universe to settle into. The other idea was this specific implementation of that general scheme based on the idea of baby universes. And so in our baby universe idea, it's not just that empty space would spit off universes toward the future, and those little baby universes would start small in a Big Bang-like configuration, then grow and increase in entropy. But they would also do the same thing toward the past. So our Big Bang in our picture is not the center of the universe or the middle, but it is the beginning of our little baby universe, and there are oppositely directed baby universes going the other way. So all of which is to say, so number one, for Joe's question, there's no possibility of arrows pointing in our model in directions other than toward the past and toward the future, because time only goes in one direction, right? Time is one-dimensional, so there is only the past and the future. Those are the two sort of directions you can move in the time direction. So There is in the far future a whole bunch of many, many universes, all of which have increasing entropy until they locally settle down to empty space. And then in the past, there's a whole bunch of universes that grow to the past and they locally increase in entropy toward the past and then settle down into empty space. So Julian Barber works in a very different context of cosmology than I do, okay? He's interested in what is called shape dynamics, which is this particular take that he and his collaborators have on general relativity. And he actually heard me talk about this stuff at a conference. And in part, he heard me talk, and again, he focused on the model that I had with the baby universes and not the general idea of entropy increasing because it can always increase. And then what he discovered was in his shape dynamics model, entropy will increase because it can always increase. Okay, so he's written several papers about that idea, and he wrote this book about this idea. And I had to remind him a little bit that we said that in our paper first. Okay, and so I take it as a different example, the same basic idea. It's incompatible because it's a different physical scenario, but it's the same spirit. And so I think it's a friendly addition to the set of ideas along these lines. Penrose in contrast, in his conformal cyclic cosmology, the arrow of time always points in the same direction, which I think is completely cheating. It requires an infinite amount of fine tuning to make that happen. It doesn't really explain the arrow of time in our universe. I do think that there are, in principle, other ways of explaining the arrow of time, but they would usually involve some principle that told you that either at the beginning of the universe or at the temporal boundaries of the universe, things had to be a certain way. It wouldn't be like a robust thing. What Jenny and I were aiming for was almost any initial conditions would lead to the following behavior. If that's what you want, as far as I know, our scenario is the only one that purports to do that. And so it's definitely, in my mind, one of the leading contenders for explaining this kind of thing. Jorge N., the letter N, asks a priority question. He says, any thoughts on the idea that velocity has a probabilistic nature? Meaning, during a unit of time, a particle has a probability p of moving a unit of space or not moving at all. During a long time interval, a particle with a high p would then be seen as having a high velocity, and vice versa for low p. An implication would be that since p has an upper bound of 1, there's an upper limit to velocity. My thoughts on that idea is I have no idea how that would work or fit in with modern physics. Number one, because at the classical level, right, if you think about the limit of physical behavior in the universe that is well described by classical mechanics, velocities don't behave probabilistically. They just obey Newton's laws completely deterministically and completely measurably. Now you can say, well, okay, quantum mechanics kicks in there, right? But in quantum mechanics, wave functions don't even have a well-defined velocity. As I mentioned earlier in the AMA, velocity in quantum mechanics is an observable feature of wave functions, but it is not a fact, a property, a characteristic of wave functions without observing them. And so it's not in quantum mechanics that velocity has a probabilistic nature, it's just that it's not well defined for almost all wave functions until you measure it, okay? So if you want to take an idea like this and make it into a respectable physical theory, I'm not sure what you're going to try to do. Either change quantum mechanics or forget about quantum mechanics and go back to some other theory. You're welcome to do that. It's a free country, but it's a lot of work to really turn an idea like that into enough mathematical background that other people can play with it and test it and ask what it would mean for experiments and things like that. John Schoening says, having previously enjoyed your talk with Jennifer Roulette on the black hole information paradox, do you think theorists will now turn their attention elsewhere since Netta Englehart's team has claimed to solve it? Jennifer and I gave a talk at the Royal Institution in London. You can find it online in YouTube, explaining the black hole information paradox. But it was a couple of years ago, before the modern advances. But let me be perfectly clear. Netta Engelhart nor her team has Neither Netta nor her team has claimed to solve the black hole information paradox. We had Netta on the podcast here. You can hear her very, very clearly say, we have not yet finished trying to do this. They have some ideas that might be relevant for eventually understanding the black hole information paradox. They might lead to a solution sooner or later, but we're not there yet. We don't have it. And so No, I do not think that the theorists are going to turn their attention elsewhere anytime soon. There's still a lot of work to be done there. Riverside says, Trump has been voted out of office partly as a result of his COVID mismanagement and his mistrust of science, which he shares with other populists. But the deep economic inequalities that allow populists like Trump to thrive are still there, and it seems to me that the USA cannot hope to maintain a cohesive democracy unless it turns itself into a more egalitarian European-style country, with a functioning social safety net and stronger fiscal redistribution. Merely safeguarding procedural democracy, which was the theme of some of your last podcasts, would not be enough. Would you agree? I don't think I would agree. I would agree with a weaker version of the statement that you made. You're making a pretty strong statement. You say that the USA cannot hope to remain a cohesive democracy unless it turns itself into a more egalitarian European-style country. That is a prediction that is far too confident for me to even imagine making. The United States, on the one hand, has been pretty robust for a couple of centuries now, and we've never been a European-style egalitarian social welfare state, right? We're less egalitarian than most European countries, at least in the last 100 years, and we've survived. Now, that it certainly doesn't mean that the United States is going to continue to survive as a cohesive democracy. I would absolutely not be surprised at this rate if things went disastrously wrong and 20 years from now or 50 years from now, we do not recognize the United States as a democracy anymore. I think that's a terrible prospect worth taking very, very seriously. I don't want to downplay it. But I certainly don't have the confidence in my own prognostication abilities to say that unless we do this specific thing, that will happen. Okay? Maybe it will happen. I'm sympathetic with the idea. I'm sympathetic with the idea that there's too much inequality in the United States. We've all seen the numbers of how, in particular, in this particular pandemic that we're trying to come out of, it has greatly increased inequality, right? People who were struggling before struggled worse during the pandemic. Billionaires who are very wealthy have done better, have increased their wealth. And I don't think that's right. That's not how pandemics should affect the economy of a country. But I also think that the issues are not precisely mapped onto income or wealth equality issues. I think that the more important issues are one of feeling that you have a say. I think that the reason why populists resonate is not because some people are poor, that has something to do with it, or difficulty getting jobs or whatever. It's because people think that they're powerless, that their voice is not being heard, that the government is going and doing its own thing in ways that they don't have any influence over, despite the fact that it's purportedly a democracy. I think that's actually the more important thing to be fixed if we want to strengthen democracy going forward. I could be totally wrong about that. Again, I'm not an expert, and maybe nobody is enough of an expert to make statements about those things with high degrees of confidence there. Eric Karstensen says, priority question, do you have an ideal world where certain historical events go differently? The ideal world I think of is where Robert F. Kennedy is never assassinated in 1968, and he goes on to become president instead of Richard Nixon, which avoids prolonging Vietnam and the Watergate scandal. Short answer is no. I don't have an ideal world. There's things that I would like to improve about the world, and so let me be more specific. There are aspects of the world which I unambiguously think could be improved by changing them in certain ways. But the question of going to certain discrete, influential historical events and tweaking them a little bit so as to bring about the world I would rather see is much more problematic. That, there you get into chaos theory and the difficulty of making predictions and things like that. So maybe if Robert F. Kennedy had not been assassinated and Nixon would not have been voted in, other things would have gone better, but maybe not. Maybe you could even say there's a 60% chance, but I don't think I could say there's a 99% chance that things would have gone better. Vietnam obviously was a problem, but JFK and Lyndon Johnson, who were both Democrats, were, running the Vietnam War for a long time. There's no obvious idea that because if Bobby Kennedy had been elected, he would have gotten us out of Vietnam. Politicians are tricky. They say things and they don't end up doing them all the time. So I don't know enough about that era to say how devoted or how influential he would have been to actually make that happen. And as far as Watergate is concerned, Watergate was an example of egregious abuse of power, illegal actions on the part of the president, but it also led to reforms of the system, the ability to have special prosecutors and things like that. So maybe it would have been worse overall if Watergate had not happened. If I were to imagine ideal histories, I would have wanted to stop some terrible massacres or tragedies or genocides, right? Like the Holocaust or various other terrible things that happened. Like there is a little bit more cut and dried to me that if that had not happened, the world would be better. On the other hand, I don't know, like if it comes to either assassinating or not assassinating one person, I'm not at all sure what would need to happen to guarantee that the Holocaust would not have happened. You can say, well, kill baby Hitler. That's the usual thing to say. But it's not at all obvious to me that the social forces wouldn't have led to something more or less similar to what actually happened in World War II. I don't know. Maybe they wouldn't have, but I just don't know. Claudio Slamovitz says about Oumuamua, the interstellar visitor we had that we talked about with Avi Loeb. While Oumuamua's speed was notably high for solar system standards, 26.3 kilometers per second relative to the sun, it's still very low compared to the speed of light. Would we have noticed anything weird had Oumuamua's dash been, say, 100 or 1,000 times faster? Is it conceivable that a material object can be accelerated to relativistic speeds by a succession of pushes from stars or other massive bodies? So it certainly would have been much weirder if Oumuamua's speed had been 100 or 1,000 times faster. So if you think about what is going on in our galaxy, the stars moving around and, with respect to each other and around the center of the galaxy, the typical speed you should have in mind is something like a couple hundred kilometers per second, okay? 200 kilometers per second, 300 kilometers per second, something like that. That's the typical speed that stars and other objects have in the galaxy. So that's the speed you expect everything to have with respect to everything else on average, okay? This is why Avi made the point that in some sense, Oumuamua's speed is anomalously low. 26 kilometers per second is lower than 300 kilometers per second. But if it had been 3,000 kilometers per second, that would be anomalously high, and that would be weird. So yes, that would be weird. Is it conceivable that something could naturally be accelerated that fast? It's conceivable, but it's very, very unlikely. Things do get pushed around by passing by stars, but it happens slowly and gradually, and every little push is very tiny, and sometimes the pushes go in opposite directions from each other, right? So you certainly do not expect things to be accelerated to very, very fast speeds. And I should go further than that. You certainly don't expect things to be accelerated to relativistic speeds near the speed of light, because once they're accelerated to the escape velocity of the galaxy, they escape from the galaxy and they are no longer being accelerated by gravitational assists from nearby stars and things like that. So there is an upper limit to speeds that you expect for things in our galaxy, namely the escape velocity, whatever that is. Farron Christou says, a priority question. You guys are using up your priority questions. Remember, only once in your life are you allowed to ask this, but I'm glad that it was a useful mechanism that we came up with. So the question is, I really enjoy your interviews with Daryl Morey and Julia Galef, and along those lines, would you consider doing an interview with an expert on the stock market? There may be no other endeavor with such a rich history of formally intersecting analytics with the study of rational-irrational decision-making. Yes, thank you for giving the suggestion. This was not a good choice, Farron, I have to say, for your priority question, because I will always take suggestions, and I will never comment on whether I will do it one way or the other. When I try to make predictions ahead of time or even aspirations, even goals for either who to have or what subjects to have, I feel like I'm locking myself into something that may or may not happen. So I personally like to just take all the suggestions I can, and whenever I get a suggestion, I will say thank you. I always like getting suggestions, but that's all I will say. I don't want to say more than that. I mean, certainly I can say, yes, this topic area is very, very interesting to talk about and to think about, like you say, the connection of intersecting analytics with decision-making. That's a good topic. Okay, I'm grouping these next two questions. One's from Liniu Miziara, who says, if a quantum particle doesn't really spin, what's the best way to define quantum spin? And Craig Stevens says, a while back you said that we could think of the spin of particles such as electrons as somewhat similar to the spin of larger objects, namely angular momentum. Thus, a spin could be considered roughly either clockwise or counterclockwise. If this is true, how are we to imagine a spin of 1/2? So, to Linu's question, it is really spin. That's what I think these days. There is lore. If you read books on particle physics or quantum field theory, people will say, we talk about spin of elementary particles, but don't think of it as really spin. It's just some component of angular momentum that is related to spin, but is not really the same. And that whole discourse sounds very weird. Like, if it is literally angular momentum, why isn't it spin? Like that sounds like a weird thing. But what they have in mind is that the electron is like a little dot, right? That is like literally a particle of zero size. And a particle of zero size can't spin, obviously. What you could do is say, well, what if we treated the electron as, let's say, a solid sphere of some non-zero size? And then what you can show is that there is no size of the electron that can spin at the right rate without going faster than the speed of light to give it the spin, the angular momentum that it actually has, given the mass that it has. But that's a little bit silly, that discourse also, because the electron is neither a little dot, nor is it a little sphere. What the electron is the excitation of a quantum field, right? The electron field. And as I mentioned on the podcast before, I think this is what Craig is getting at. When you legitimately think of the electron as a field, fields can have angular momentum, depending on the field configuration. Even a stationary field can have a certain amount of angular momentum, and basically you should and can should think of the spin of the electron as an amount of angular momentum contained in the electron field. So that is the best way to think about it. It really is something spinning in some very real sense. To Craig's question, how are we to imagine a spin of 1/2? Well, remember, the 1/2 is a bit of a convention, right? It's not that the spin of the electron is 1/2, it's that it's 1/2 times h bar. H bar is Planck's constant, h divided by 2 pi, okay? So Planck's constant is a universal constant in quantum mechanics. It appears in the Schrödinger equation and elsewhere. It appears so many times that we often set it equal to 1. That's why we say a spin 1/2 particle. What we really mean is a spin h bar over 2 particle. And if we had defined h double bar to be h over 4 pi, okay, then in units of h double bar, the electron spin would be 1. And the spin of the photon would be 2. And rather than talking about spin 1/2 particles versus spin 1 particles, we talk about odd spin particles versus even spin particles and so forth. So there's nothing special about or mysterious or weird about the spin of 1/2 in that particular context. Jeff B says, actually, wait a minute. I'm just realizing now, sorry, Craig, I'm realizing that there's a deeper level to your question, which is probably what you had in mind, that it sort of skipped by me. Angular momentum in forms other than the spin of individual particles does only come in integral values of h bar, right? So what I mean by that is, if you have an electron in an atom, the electron can have spin, which is angular momentum, but it can also be orbiting the atom with a certain amount of what we call orbital angular momentum. And unlike the spin of elementary particles, the orbital angular momentum is only always an integer in units of h bar. So probably what you're asking is a more sophisticated question than I gave you credit for. Sorry about that. How can the spin of elementary particles take on these different allowed values that orbital angular momentum cannot take on? So that's a much harder question to answer, and it has to do with the nature of the topology of the Lorentz group, okay, and the group of rotations in 3 spatial dimensions. There are relationships between objects in 3 spatial dimensions with the feature that if I rotate them 360 degrees, they don't come back to where they started. So I'm being very vague because it is not a physical thing. If you take like a physical thing like a coffee cup and you rotate it 360 degrees, it comes back to where you start. But if you think about the relationship between the coffee cup and yourself, if you rotate it without moving your hand, without letting go of it, it will come back only when you do a rotation of 720 degrees, 2 rotations of 360 degrees. So topologically, the different kinds of rotations that you need to do to get an object back to where it started, classically only are 360-degree rotations, but quantum mechanically there is the possibility of having objects or fields or whatever that only come back to where they started when you rotate them twice around the circle, 720 degrees. That is, on the one hand, what we mean by spin 1/2, and it is also realized by electrons and quarks and neutrinos and so forth. If you want more details than that, a tiny bit more detail is in my YouTube lecture in the biggest ideas of the universe. I think the one called Matter. Why in the world is it in the one called Matter? Because the one called Matter is really about the spin statistics theorem and how the fact that particles of different spins are either bosons that pile on top of each other or fermions that take up space. If you want much more detail than that, then I would Google around spin statistics theorem and things like that. It is a fascinating but quite tricky and subtle story. Sorry not to be more definitive than that. Okay, Jeff B. says, in your Biggest Ideas series, you mentioned that space and time are different because it is not unusual for objects to very abruptly end in space, but it would be surprising to see an object abruptly end in time. You went on to explain that we measure distances in space differently than we measure intervals in space-time, but I'm not sure how this explains why we don't see objects abruptly end in time. Is it possible to paint an intuitive picture for why objects behave this way? So I'm not sure if I'm going to be able to do justice to what you're asking. It's a perfectly good question. It's a very, very good question. Why do we have some continuity over time in ways that we don't have continuity over space? So for those of you who don't know what I was talking about in those lectures, like the desk right in front of me as I'm talking into this microphone here, it exists here where I'm pointing my finger, and it doesn't exist here right next to it, right? There's an abrupt edge to the desk. There is no rule in physics that says if there's a desk at this spatial point x, there's probably more desk at spatial point x plus delta x. But there is a rule in physics that says if there is a desk at time t, there is probably something desk-like, probably a desk in fact, but at the very least something that was created from the pieces of the desk at time t plus t, delta t. And, you know, in some sense, that comes down to that's how the laws of physics are. The laws of physics relate stuff at different moments of time, okay? You can be a little bit more specific by appealing to conservation laws. Noether's theorem says that when there is a symmetry, there's a conservation law. And so you get conservation laws from time translation invariance, for example, conservation of energy. And what that means is conservation of energy over time. There is a number you can define by integrating the total amount of energy at one moment of time, and that stays more or less fixed from moment to moment. Take that, plus the fact that the laws of physics are local. If I poke something here, the physically observable consequences of that poking do not instantaneously spread throughout the universe. They travel no faster than the speed of light. Together, those things imply that if you have conserved energy and you can't change things at rates faster than the speed of light, that if there is something here now, there's something similar to it, the same amount of energy, a moment later. Okay. Now you can always ask, well, why are there conservation laws? Why are there symmetries, etc.? That's a deeper question. But as we said before in the podcast, at some level you're going to bottom out and you're going to say that is because that's how the laws of physics are. Another angle on saying the same thing would be there's only one direction of time. There's multiple directions of space. So there is at least the possibility that there's this continuity along the one dimension of time where continuity in space would have to mean everything is just uniform everywhere in the universe, and that really wouldn't make quite as much sense. Wouldn't be as fun a universe to live in anyway. Okay, Johnny says, is there anything from your work that has changed how you live your life? In other words, does knowing the intricacies of how matter works modify the way you make choices or conduct yourself in the world? Well, I guess there's two levels to this question. One is, the detailed level of, knowing the standard model of particle physics, do you interact with the world differently? No, not really. Like, it doesn't really help me drive a car or play basketball or anything like that, right? That's a far too microscopic level of knowledge to be very helpful in the macroscopic world. It's nice to know that energy is conserved and momentum is conserved and entropy increases and things like that, but you can do pretty well in life without knowing those things. I do think that at the deeper level or the more meta level, knowing and thinking carefully about the laws of physics and the way that nature works does affect how I think about life, right? How I think about what life is, the meaning of life, the morality of different actions, what will happen when life ends, all of those things, which are very important things, right? These are important things, and they're metaphysical questions in some sense. And to me, metaphysics is extremely informed by physics. How could it be any other way? So not that there's a simple direct line that I can draw between the two sets of questions, but I certainly think that one affects the other in important, intricate, complicated ways. Okay, Lou Argyres says, I don't know how to pronounce your name. Sorry about that, Lou. Argyres says, is there anything interesting to say about gravitons in the absence of a theory of quantum gravity? For instance, can a graviton escape from a black hole? Yeah, there's plenty of interesting things to say about gravitons because even though we don't have a full theory of quantum gravity, we do have two things. Namely, we have a good theory of classical gravity, general relativity, and we have quantum mechanics. And there are very basic, robust features of what happens when you take a classical theory and you quantize it in some sense. So there will be gravitons. If you believe in general relativity and you believe in quantum mechanics, you should believe in gravitons. To believe in gravitons does not mean that you need to think you have a full theory of quantum gravity or any full, complete, robust understanding of what space-time even is. There are things called phonons. You've heard of photons, right? Photons are the particles of light. But we also have, in addition to classical electromagnetic waves, which you then quantize to get photons, we have classical sound waves, right? There are classical waves that you're listening to right now when you're listening to my voice. You could ask, could you quantize them and get particle-like excitations of sound? The answer is yes, absolutely, because you don't need to know that the sound wave is made out of some atoms bumping into each other. There's a higher level emergent theory of a fluid, the gas in the air that has equations that it obeys, and you can quantize those equations and show that there are particle-like excitations in them. Same thing is true with gravity, no matter what the fundamental theory is. Can gravitons escape from a black hole? No, because gravitons don't equal gravity. Okay, just like photons don't equal electromagnetism. Photons are the particle-like excitations of the electromagnetic field. If you have a big classical coherent field around a charge, like a charge around an electron, you shouldn't think of that as a set of photons. There's nothing changing. It's just some big Coulomb electromagnetic field that's sitting there unchanging. Whereas a photon is a ripple, right? Is a vibration that is traveling at the speed of light. Likewise, black holes have gravitational fields that are there, and we can define them and measure them, and we've seen their effects. A graviton would be a tiny ripple propagating at the speed of light over and on top of that classical background field. And since they move at the speed of light, they cannot escape from black holes, because you cannot escape from a black hole unless you move faster than the speed of light. All right, I'm going to group two more questions together. Robert Ruxandrescu says, priority question. Imagine a situation where you have a particle in superposition. Its wave function says there's a 50% chance of finding it in place A and 50% chance of finding it 1,000 light years away in place B. My question is, what's the gravitational field going to do in this situation? Say you don't measure the particle so you don't disturb its superposition state. Instead, you simply observe the gravitational field. What's the gravitational field going to do? And Gregory Mendel says, here's a gravity and decoherence question. You measure an electron spin in St. Louis. Heads, you go to New York. Tails, you go to LA. Your spouse on the far side of the moon uses a torsion balance to measure the tidal force you produce. Does the torsion balance show you're in one location, New York or LA, or both at the same time? So in both cases here, gravity is a bit of a red herring in both of these questions. You could have asked exactly the same question about electromagnetism, right? Charged particles have electromagnetic fields that are very much like the gravitational fields of little particles. So particles have fields around them. And when it comes to decoherence and so forth, for many purposes, you can think of the fields attached to particles, whether they're the electric fields for charged particles or the gravitational fields for particles with energy, as part of the particle, right? Because they go along with it. You cannot separate an electron from its electric field. You cannot separate a planet from its gravitational field, okay? So when you say, well, I observe the gravitational field of the particle, but not the particle itself, the answer is that's just as good as measuring the particle itself. In this case where there's a superposition, where there's a particle in a superposition of being at A or B, the gravitational field of the particle is in a superposition of being around A and around B. And if you measure it, you're only going to find it near A or near B, and then you've branched the wave function of the universe. Similarly, for Gregory's question, once you do that, you measure an electron spin and then you move, you go to New York or LA, depending on the outcome, you're a big macroscopic thing, okay? You're decohering all the time. You are not staying in a superposition of going to New York and staying in LA, okay? You have branched the wave function of the universe, and your spouse on the far side of the moon has branched along with it. So the answer is your spouse there's two copies of your spouse, just like there's two copies of you. There's a you that goes to New York and a spouse on that branch of the wave function. There's a you that goes to LA and a spouse on that branch of the wave function. And either one of them, if they use a torsion balance very carefully to detect where you are, will uniquely detect where you are on that branch of the wave function. Okay, Moshe Fader says, in 2016, astronomers Konstantin Batygin and Michael Brown proposed explaining unexpected clustering in the Kuiper belt with a hypothetical planet 9 5 to 15 times larger than the Earth. In 2018, Amir Siraj and Avi Loeb proposed an alternative, the existence of a primordial black hole in the outer solar system and a method for the new Vera Rubin telescope to search for it. What prior probability distribution do you assign to the black hole idea? So just in case you don't know, Moshe, Michael Brown was one of the first guests on the Mindscape podcast. Mike is a good friend of mine at Caltech, so is Konstantin. And Mike talked about both killing Pluto, as we talked about earlier, and also perhaps replacing it with a real planet out there, which they call Planet 9. To me, sure, it's possible. You can always replace a planet that is too far away to see with a black hole that is too far away and too small to see. That is difficult to disprove an idea like that. But I think that the prior probability distribution you should assign to that is really, really small. Why? Well, we know of lots of planets, and we know of lots of planet-like things. We don't know of any tiny primordial black holes. Any, right? We know of big black holes that were made by collapsing stars and so forth, but we've never seen any primordial black holes. So I would put the prior on that as pretty darn small. Okay, I think I'm grouping two more questions together here. Anonymous says, Google AI researcher Francois Chollet recently tweeted, within 10 to 20 years, nearly every branch of science will be, for all intents and purposes, a branch of computer science. Is this something you'd agree with? Do you think you'll be having to use more computer science AI for research in the future? And then Dan Inch says, it is fascinating how the Schrödinger equation is empirically correct and yet still needs an interpretation. Could we feed all the physics data we have into a very powerful computer, wait until it finds the systems of equations that can generate all the data, and then work backwards to place our interpretation on whatever the equations are? If we could, what would our extra interpretations really be adding? So I group these two together. There's a slight connection between them, but I want to use Dan's question to answer Anonymous's question. The Schrödinger equation doesn't need an interpretation at all. It's an equation. It says that here's a function and here's how the function evolves over time, okay? What we need an interpretation for is to say, in what sense, in what way does that equation describe reality? And that question is one that computers, even very powerful ones, are not good at answering. So a computer might very well be able to invent the Schrodinger equation, but that's not the problem. I mean, Schrodinger did that like on vacation, literally. Like he was in the Alps and he invented the Schrodinger equation. No surprise that a computer would be able to do that. Max Tegmark, who was on the podcast, is literally generating AI programs that are trying to do exactly that, come up with new laws of physics based on curve fitting to the data. But science is enormously more than curve fitting, okay? Enormously more than looking for an equation that packages the data in a simple and compact form. We need to understand what is going on, right? That's why there's more to science than just fitting the data. So I think that all of the issues with quantum mechanics are not from we don't understand the Schrodinger equation, but that the empirical reality of quantum measurement doesn't seem to be described by the Schrodinger equation. Now, Everett or Many Worldser says, well, really it is, but you're not seeing the whole wave function, and that's perfectly legitimate. But to at least the point of view of any one observer, the Schrodinger equation is not up to the task of describing quantum measurement. That's why you need more than that. That's why it's not just a task for a computer. And so therefore, for Anonymous's question, I mean, it's very charming that a computer scientist thinks that in the future, all science will be a branch of computer science, but I can't agree with that, okay? I do obviously agree that there will be more and more computer work in science. That's already happening. You know, you don't need to wait 10 or 20 years. That was happening 20 years ago or longer than that. But there will still be plenty of room for doing something more than that. I don't even use computers that much in my science, a little bit, but my kind of science isn't going to change that much at all. I do think that there'll be more and more computer science, like I said, artificial intelligence, especially because we have these big data sets and we're searching for patterns in them. So I see what the computers are doing. The most obvious use for computers is something kind of like Kepler, right? If you think about what Johannes Kepler did, you had Tycho Brahe before him, who collected a lot of data. It was the first big data era in astronomy, Tycho looking at the positions of planets on the sky, okay? And Kepler did the curve fitting. Kepler was the one who came along and said, it's not circles and epicycles, it's ellipses, right? And ellipses describe the motion of planets in the solar system. But they weren't done. That wasn't the end of planetary science, right? Because you could say, well, why? Why is it ellipses? And that's where the real excitement came with Newton and other people saying there's an inverse square law of gravity, there are laws of motions that explain why the motion is ellipses. So the computers would be really good at finding the ellipses. They would be terrible at, or at least, I shouldn't say they'd be terrible. I'm completely open to the idea that someday computers will be much better than human beings at this. But my point is, there's a qualitatively different kind of question being asked that is much less well suited for computers as they are today when you come to explaining why the numerical relations that we find in the data are there. So I don't see any need to worry that in the next 10 to 20 years, that kind of work is going to be outsourced to computers away from scientists and philosophers and so forth. Okay, Murray Dunn says, as part of a previous AMA answer, you explained why the net charge of a topologically closed universe would be zero, but you also mentioned that the net energy would be zero as well. Can you explain why that is the case? I can try. Think of a topologically closed universe as a sphere. And there are other more complicated topologies it could have, but it's a simple visualization, right? So just imagine a two-dimensional sphere. Keep our lives easy. Imagine the world was two-dimensional. So the thought experiment is put a positive electric charge. We'll do it for electric charge first. Positive electric charge on the north pole of the sphere and say, I'm only putting that positive electric charge on the sphere, no other charges. The point is that the lines of electric field from that charge need to go somewhere, right? They emanate away from the electric charge. If it's a positive charge, the electric field points away from it, but then they go around the sphere and they focus back on the South Pole if you put the charge at the North Pole. So what you have at the South Pole is a bunch of electric field lines pointing inward and then ending. What that means is there is a negative charge there. You can define a negative charge as the place where electric field lines point into an end. That's what it is. So that's the proof in slightly hand-wavy form for why the net charge of a closed universe must be zero. Same exact thing happens for gravity, but replace lines of gravitational acceleration with lines of electric field, right? If I put a mass at the top of the sphere, there's a gravitational pull toward the mass, and I follow those lines backward. What it means is that at the South Pole, there's a gravitational push, okay? Which means that there needs to be a negative amount of mass, a negative amount of energy, and the net energy has to be zero. This all comes down to Gauss's law and Stokes' theorem in the world of differential geometry, but I think it's pretty easy to understand just in terms of those pictures. Josh Hedgepeth says, mine is a philosophical quandary. Have you ever played the lottery using a quantum random number generator, and if not, why? Even if you are no more likely to win, does it still increase the fraction of worlds where some variant of you does win, as opposed to if you just didn't bother? It's the type of thing where you don't play to win, you play to create. As I said before, in my mind, even though I'm a many worlds person, the upshot of many worlds is that for actual human beings in these many sets of worlds, all of their expectations and all of their actions and all of their rules for living life should be exactly the same as if they lived in a truly stochastic single world. That is the conclusion that you reach from thinking carefully about the philosophy of many worlds. So yes, if you made a quantum random number generator to play the lottery, you would, if it were a fair lottery, etc., you would guarantee that on some branch of the wave function you would win. But you would also guarantee that on many, 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 many branches of the wave function you would lose, if it's a big lottery, right, like Powerball or whatever. And so, yeah, on some branch you win a whole bunch of money, on other branches you lose a couple bucks. And so the net outcome is that the total numbers of yourselves lose money, right? Because the government doesn't do these lotteries for free. They're making money by doing these lotteries. So yeah, I don't want to do that. And it's exactly the same reasoning for why I don't want to play a single lottery in the single world if that's what only existed. The expectation value is against you there. Preston says, what precisely makes the task of developing a quantum theory of gravity so daunting or impossible? Are enough people working on it seriously? How long do you predict it will take? Well, there are plenty of people working on it. That's absolutely true, which is weird in some sense. It wasn't true in the 70s or 60s, right? There were very, very few people working on quantum gravity, even though people knew both about quantum mechanics and about gravity, okay? And the difference is that in 1984, we realized there was a promising theory of quantum gravity, namely superstring theory. Before that, what people said was, look, gravity is too weak. We can't get any data about it. We can't create gravitons in our laboratory. So sure, we need quantum gravity, but it's just too hard. So we're not going to expend a lot of effort trying to do that. Whereas once string theory became popular, people said, well, maybe, even though we don't have a lot of data, we have this very promising theory. Maybe we can get lucky and just think our way into the right answer. So that may or may not be true, depending on your opinions about string theory, but that was the motivation for so much quantum gravity effort going on right now. Why is it hard? Well, no one ever said it should be easy. So my individual idiosyncratic take on why it's hard is because people keep trying to quantize classical theories. And my takeaway from things like black hole information and holography and complementarity and all the thought experiments that have been done over the last few decades is quantum gravity will not arise from quantizing a classical theory of spacetime. And I'm not the only person to think this. Tom Banks and Willy Fischler are two other physicists who have really pushed this idea. I mentioned Tom before because he's an epistemic person when it comes to quantum mechanics, but very, very smart person thinking about quantum gravity and field theory and quantum mechanics. And he's made the point, based on ideas from Ted Jacobson and others, that we shouldn't start by quantizing gravity. We should do something else. And so he and I have gone in different directions about what we do, but we take that as a good starting point. But very few people do. Most people just start with some classical theory and quantizing it. That's my guess. It's more detailed than that. I mean, the point is not just that strategy doesn't work, because that strategy worked pretty well for electromagnetism and the standard model, starting with the classical theory and quantizing it. There are specific features of gravity, the lack of perfect locality and things like that, the lack of a background space-time to work with, that make that conventional procedure not work as well. How long do I predict it will take? I have no idea. Literally no idea. It could be done 5 years from now, or it might not be done 500 years from now. I really don't know. Marian Marcali says, at the largest scales, is it likely that the universe has enough complexity, diversity of structures, and coupling mechanisms for yet another higher level of organization, computation, or intelligence? For lack of a better term, since it would be as different in character as our intelligence to molecular dynamics. So this is a good question. I really, really like this question. It's an important kind of thing to think about, is in our everyday experience of intelligence and consciousness, we're used to dealing with organisms, right? With individuals, with biological beings, and they have some very, very definite notion that this is the individual and this is the rest of the world. Could you imagine the emergence of what you would recognize as intelligence or agency, but at a much larger scale, so that the big thing that we were calling intelligent was as much bigger as us as we are to our cells, okay, to our individual biological cells? So I'm very open to the idea that you can do this on an intermediate scale, right? Like you could have some super organism that was made of, let's say, 1 billion human beings or 1 billion human being sized alien organisms or something like that. That's fine. That's a sort of, on the scales we're talking about here, that's a minor increase in size. But if you're really thinking astrophysically, like could a galaxy attain intelligence in some kind of way, there's a huge problem, namely the time scales. It's not the distance scales that get in the way, it's the speed of light that gets in the way. It takes tens of thousands of years for a signal to travel from one end of the galaxy to the other. So I haven't done this thought experiment, but if you take, however long it takes a neural signal to get from our head to our feet, whatever fraction of a second that is, and compare that to our lifespan of 100 years, right? So divide those two numbers by each other, and then take the, 50,000 years it takes a light signal to go across the galaxy, and boot that up to a certain number of years. It'll be much, much longer in the age of the universe, I think, I'm pretty sure. So the point is that there's just not enough time, forgetting about the fact that it took billions of years for we human beings to evolve through natural selection, right? The universe will run out of steam before there is enough time in it for truly astrophysically large systems to become intelligent. I see no objection to it in principle, once again, but our universe is not static. It's expanding. It's emptying out. Stars will stop shining in 10 to the 15 years. So there is a finite amount of time available for complex structures to arise, and I just don't think there is enough time for truly astrophysically big structures to attain the level of complexity and structure and organization that we would recognize as conscious. Okay, slightly similar question. This will be the last question of the AMA from Raphael Rusitska. And it is, I thought a lot about this one recently. If increasing entropy is a fundamental feature of time itself, higher entropy equals more configuration possibilities, meaning chaos. Humans emotionally yearn for some form of the easier, more structured, less chaotic, ordered life. Aren't the laws of nature itself against this emotional want? And we need to accept that everything, I mean everything we take for granted, will at some point become more unstructured and chaotic, and will we need to develop ever more capabilities of dealing with ever more interdependent chaos centers? So this is a complicated question. It's a good question. I'm glad you asked it. It's complicated in an interesting and fun way. The first thing that I feel the need to say is, entropy is increasing in the universe, but there's a long way to go before we're anywhere close to maximum entropy, okay? Even, the sun shining, our sun is going to keep shining in a more or less similar way as to what it's doing now for another 5 billion years. So on the timescale of a human life, we don't recognize any profound difference in the total entropy of the universe from our birthday to our death day, okay? So I don't think that you need to worry that we're just being surrounded by more and more chaotic, low entropy or high entropy things, because we are not a closed system here in the biosphere of the Earth. We're an open system that is very, very far away from thermal equilibrium. Once the sun dies and we reach the heat death of the universe, that's a different story. That's a long way in the future. But also, I wanted to comment on the presuppositions earlier in the question, that humans emotionally yearn for some form of the more ordered life. I don't think that's true. I think it's an oversimplification of something that is true, but is a bit more complicated. Per Bach, who was one of the pioneers of thinking about complex systems and self-organized criticality and things like that, characterized complex systems as living on the edge of chaos. So this is the important thing. And, Benoit Mandelbrot would say similar things. Stuart Kauffman would say similar things. There's a limit where everything is very, very simple and everything is very, very orderly, like a checkerboard, right? Chessboard, where everything is literally, there's a square, different color, nothing is going on except this very, very simple pattern. There's another limit where things are just completely random, where rather than a checkerboard where if you're on a black square, you know that all the squares around you are white, if you move in vertical or horizontal directions. If you're on a completely random board, then knowing what the color of one square is tells you nothing about the squares next to it. Neither one of those limits is interesting in the sense of biological organization. Where you have interestingness is in between. That's the edge of chaos. So you have some structure, but not perfect rigidity. Okay, and we are not only do human beings feature that kind of in-between level of structure, but we live off the fact that the Earth is very far from thermal equilibrium, right? That's what lets us maintain this very far from perfectly ordered or perfectly chaotic in-between state. So, like I say in many different talks, in many different contexts, the second law of thermodynamics and the increase of entropy is not our enemy as living, breathing beings. It's our friend. It enables us to live and to breathe. It gives us a resource that we depend on and survive because of. And we have, again, another several billion years worth of it just because the sun is shining, a hot spot in a dark sky. So life is much more interesting and intricate than just avoiding chaos or something like that. Life is about having a little bit of chaos, but not too much, which is a lot more fun, a lot more challenging, but a lot more rewarding way to live. And with that pseudo-profound thought, that's the end of the AMA for this month. Thank you to all the Patreon supporters for supporting Mindscape. I really appreciate it. And to everyone, thanks for listening. I appreciate that too. Take care. Bye-bye.